loud. But when you're home again, you're drawn out a crowd. Try as they may, they can never define what's been said between your heart and mine. The smile on your face lets me know that you need me. There's a truth in your eyes saying you'll never leave me. The touch of your hand says you'll catch me wherever I fall. You say that when you say nothing at all. The smile on your face lets me know that you need me. There's a truth in your eyes saying you'll never leave me. The touch of your hand says you'll catch me wherever I fall. You say it best when you say nothing at all. Smile on your face, the truth in your eyes, the touch of your hand lets me know that you need me. You say it best when you say nothing at all.
There goes my heart beating, 'cause you are the reason I'm losing my sleep. Please come back now. There goes my mind racing, and you.
Universitas Gadjah Mada, or UGM, is a public university renowned as the People's University, which strives for and puts forward the interests of the citizens and nation of Indonesia. As a higher education institution that has long been recognized by the society, we are proud of our timeless and tireless dedication to the nation. By cultivating, implementing, and leveraging education, research, and community services, which constitute the salient objectives of Indonesian higher education, or Tridharma, we remain committed to incessantly promoting the values of Pancasila. We exert the utmost effort to protect Indonesia's sovereignty in accordance with Pancasila ideology and the 1945 Constitution. As a world-class university, UGM is devoted to the interests of the nation and humanity. We conduct research, provide education, and deliver community services by enhancing knowledge that benefits the community, the nation, and the world. We have been learning from one another and get stronger together, since we believe that knowledge is not useful unless it is shared with others. The learning process will never cease developing. At UGM, We learn by continuously exploring sciences, learning from history, observing the present, and researching for the future. We always work hard and never give up. The learning and research processes at UGM continue to run together and explore state-of-the-art innovations. To create a convenient, environmentally friendly, and pollution-free green campus, UGM has built a wisdom park that substantiates the teaching and learning process. The park per se is open to the public. UGM has also developed drinking water facilities throughout the campus, provided by a Drinking Water Supporting Unit. This system is harnessed by the entire academic community of UGM. As the manifestation of its teaching endeavor, UGM operates various field laboratories for educational and research purposes. Furthermore, UGM has established and run a science technopark as an embodiment of its capability of inventing and commercializing a myriad of innovative health products, ranging from medical devices, herbal medicines, and healthy food.
There are now more than 118,000 cases in 114 countries, and 4,291 people have lost their lives.
2020 has been a tough year for anyone, and it is no exception for UGM. Campus activities are abruptly halted, student activities on campus are annulled, and everyone is forced to work, worship, and study from home. Lecturers have no choice but to learn how to teach effectively using the Information and Communication Technology or ICT. Learning and research on technology are strongly supported at UGM, and in fact, we have conducted various cutting-edge technological research. Community Service or KKN is one of the most important courses to complete the study program, which will be undergone by University of Gadjah Mada or UGM in 2020 while adapting online courses system. Supported by the Ministry of Education, UGM will continue its service within the society across Indonesia during the pandemic issue. Lecturers and researchers at UGM continue carrying out basic and applied research in many realms. For instance, studies in the health sector to cope with COVID-19 are being encouraged and accelerated as a form of UGM's commitment to mitigating disaster using scientific methods. One of the most innovative inventions regarding to mitigating the COVID-19 is GINOS, a screening tool or early detector of patients exposed to COVID-19, which is able to identify the symptom through exhale within 80 seconds. GINOS is highly reliable. It has a number of advantages as a COVID-19 fast detection tool. Its sensor is able to detect more than thousands of patients in the long term, while providing relatively fast results, non-invasive and affordable. In addition, its usage also applies non-rebreathing mask and disposable HEPA filter. Those challenges somehow direct or even force us to innovate and modify approaches. Success is a journey which necessitates smart work through learning, studying, and sacrificing. Despite all that, most of all, we love what we do.
has embarked on the path to an electric vehicle ecosystem by launching the Battery Electric Vehicle Program, or KBLBV. To accelerate the program, the State Electric Company, PLN, has developed an application called Chargin, the first app to support the electric vehicle ecosystem in Indonesia. Chargin controls and monitors electric car or motorbike battery charging at public electric vehicle charging stations, or SPKLU. Chargin is easy to use. Users can directly download the app onto their smartphones and manage their balance via the Link Aja payment platform. Chargin will guide the user to the nearest SPKLU location. At SPKLU, connect the charger to the vehicle's electrical charging inlet. Open the Chargin application and select the charging menu. Then, scan the barcode that is located at the top of the charger connector. Enter the amount of kilowatt hours to purchase. Click reservation, then confirm the charging. The light indicator on the charging connector will turn on and then turn off once the charging process is complete. Chargin makes charging electric vehicles easier and more practical, convenient, and efficient.
Kalau Anda ingin memanfaatkan SPKLU atau stasiun pengisian kendaraan listrik umum milik PLN, itu bisa dengan aplikasi Charge-in yang bisa di-download di Google Play Store. Di situ ada lokasinya SPKLU PLN itu di mana aja dan mesin yang masih ready di mana. Dan kalau Anda register nanti Anda bisa dapat barcode dan tinggal scan-kan barcode tersebut ke SPKLU dan Anda bisa mengecas mobil listrik Anda.
Transformasi PLN, Power Beyond Generations.
Dengan PLN Mobile, semua makin mudah. Download aplikasinya sekarang juga. PLN, Power Beyond Generations.
Corporations can use two approaches to increase value: maximizing revenue and reducing cost. PLN is also expected to reduce cost and increase operational efficiency. Enterprise Asset Management, or EAM, is an important instrument to improve efficiency, especially during transmission and distribution. There is an abundance of data and information that must be integrated to make real-time decisions accurately. With EAM, PLN can aim to reduce operational and maintenance costs by up to 1.3 trillion IDR for distribution and 419 billion IDR during transmission activities by 2024. EAM is achieved through integrated maintenance from planning, execution to budget utilization, with a target of reducing the duration of blackouts within 1 year. This method can reduce unplanned outages, which inevitably lead to increased cost and decreased customer trust. To accelerate accurate decision-making, data and operational maintenance activities are converted into digital form with easy-to-understand visualizations. This allows PLN to provide reliable and high-quality electricity. addition, PLN is developing a real-time loss monitoring initiative, aiming to reduce potential energy loss that can save up to 562 billion IDR by 2024. Real-time loss monitoring is PLN's effort to reduce potential loss of electrical energy from upstream to downstream due to leakage. Mitigating energy leak will improve the quality of analysis and accuracy of each energy transaction. This gives PLN the potential to earn an additional revenue of 37 billion IDR per year by 2024 at a B2B rate. By providing services without power outages and no flicker.
Transformasi PLN, Power Beyond Generations.
Universitas Gadjah Mada or UGM is a public university renowned as the People's University, which strives for and puts forward the interests of the citizens and nation of Indonesia. As a higher education institution that has long been recognized by the society, we are proud of our timeless and tireless dedication to the nation. By cultivating, implementing, and leveraging education, research, and community services, which constitute the salient objectives of Indonesian higher education, or Tridharma, we remain committed to incessantly promoting the values of Pancasila. We exert the utmost effort to protect Indonesia's sovereignty in accordance with Pancasila ideology and the 1945 Constitution. As a world-class university, UGM is devoted to the interests of the nation and humanity. We conduct research, provide education, and deliver community services by enhancing knowledge that benefits the community, the nation, and the world. We have been learning from one another and get stronger together since we believe that knowledge is not useful unless it is shared with others. The learning process will never cease developing. At UGM, we learn by continuously exploring sciences, learning from history, observing the present, and researching for the future. We always work hard and never give up. The learning and research processes at UGM continue to run together and explore state-of-the-art innovations. To create a convenient, environmentally friendly, and pollution-free green campus, UGM has built a wisdom park that substantiates the teaching and learning process. The park per se is open to the public. UGM has also developed drinking water facilities throughout the campus, provided by Drinking Water Supporting Unit. This system is harnessed by the entire academic community of UGM. As the manifestation of its teaching endeavor, UGM operates various field laboratories for educational and research purposes. Furthermore, UGM has established and run a science technopark as an embodiment of its capability of inventing and commercializing a myriad of innovative health products, ranging from medical devices, herbal medicines, and healthy food.
There are now more than 118,000 cases in 114 countries, and 4,291 people have lost their lives.
2020 has been a tough year for anyone, and it is no exception for UGM. Campus activities are abruptly halted, Student activities on campus are annulled, and everyone is forced to work, worship, and study from home. Lecturers have no choice but to learn how to teach effectively using the Information and Communication Technology or ICT. Learning and research on technology are strongly supported at UGM, and in fact, we have conducted various cutting-edge technological research. Community Service or KKN is one of the most important courses to complete the study program, which will be undergone by University of Gadjah Mada or UGM in 2020 while adapting online courses system. Supported by the Ministry of Education, UGM will continue its service within the society across Indonesia during the pandemic issue. Lecturers and researchers at UGM continue carrying out basic and applied research in many realms. For instance, studies in the health sector to cope with COVID-19 are being encouraged and accelerated as a form of UGM's commitment to mitigating disaster using scientific methods. One of the most innovative inventions regarding to mitigating the COVID-19 is GENOS, a screening tool or early detector of patients exposed to COVID-19, which is able to identify the symptom through exhale within 80 seconds. GENOS is highly reliable. It has a number of advantages as a COVID-19 fast detection tool. Its sensor is able to detect more than thousands of patients in the long term, while providing relatively fast results, non-invasive and affordable. In addition, its usage also applies non-rebreathing mask and disposable HEPA filter. Those challenges somehow direct or even force us to innovate and modify approaches. Success is a journey which necessitates smart work through learning, studying, and sacrificing. Despite all that, most of all, we love what we do.
The Indonesian government has embarked on the path to an electric vehicle ecosystem by launching the Battery Electric Vehicle Program, or KBLBV. To accelerate the program, the State Electric Company, PLN, has developed an application called Chargin, the first app to support the electric vehicle ecosystem in Indonesia. Chargin controls and monitors electric car or motorbike battery charging at public electric vehicle charging stations, or SPKLU. Chargin is easy to use. Users can directly download the app onto their smartphones and manage their balance via the Link Aja payment platform. Chargin will guide the user to the nearest SPKLU location. At SPKLU, connect the charger to the vehicle's electrical charging inlet. Open the Chargin application and select the charging menu. Then, scan the barcode that is located at the top of the charger connector. Enter the amount of kilowatt hours to purchase. Click reservation, then confirm the charging. The light indicator on the charging connector will turn on and then turn off once the charging process is complete. Chargin makes charging electric vehicles easier and more practical, convenient, and efficient.
Kalau Anda ingin memanfaatkan SPKLU atau stasiun pengisian kendaraan listrik umum milik PLN itu bisa dengan aplikasi Charge In yang bisa di-download di Google Play Store. Di situ ada lokasinya SPKLU PLN itu di mana aja dan mesin yang masih ready di mana. Dan kalau Anda register nanti Anda bisa dapat barcode dan tinggal scan-kan barcode tersebut ke SPKLU dan Anda bisa mengecas mobil listrik Anda.
Transformasi PLN, Power Beyond Generations.
Dengan PLN Mobile, semua makin mudah. Download aplikasinya sekarang juga. PLN, Power Beyond Generations.
Corporations can use two approaches to increase value: maximizing revenue and reducing cost. PLN is also expected to reduce cost and increase operational efficiency. Enterprise Asset Management, or EAM, is an important instrument to improve efficiency, especially during transmission and distribution. There is an abundance of data and information that must be integrated to make real-time decisions accurately. With EAM, PLN can aim to reduce operational and maintenance costs by up to 1.3 trillion IDR for distribution and 419 billion IDR during transmission activities by 2024. EAM is achieved through integrated maintenance from planning, execution to budget utilization, with a target of reducing the duration of blackouts within 1 year. This method can reduce unplanned outages, which inevitably lead to increased cost and decreased customer trust. To accelerate accurate decision-making, data and operational maintenance activities are converted into digital form with easy-to-understand visualizations. This allows PLN to provide reliable and high-quality electricity. In addition, PLN is developing a real-time loss monitoring initiative, aiming to reduce potential energy loss that can save up to 562 billion IDR by 2024. Real-time loss monitoring is PLN's effort to reduce potential loss of electrical energy from upstream to downstream due to leakage. Mitigating energy leak will improve the quality of analysis and accuracy of each energy transaction. This gives PLN the potential to earn an additional revenue of 37 billion IDR per year by 2024 at a B2B rate. By providing services without power outages and no flicker.
Transformasi PLN, Power Beyond Generations.
Universitas Gadjah Mada or UGM is a public university renowned as the People's University, which strives for and puts forward the interests of the citizens and nation of Indonesia. As a higher education institution that has long been recognized by the society, we are proud of our timeless and tireless dedication to the nation. By cultivating, implementing, and leveraging education, research, and community services, which constitute the salient objectives of Indonesian higher education, or Tridharma, we remain committed to incessantly promoting the values of Pancasila. We exert the utmost effort to protect Indonesia's sovereignty in accordance with Pancasila ideology and the 1945 Constitution. As a world-class university, UGM is devoted to the interests of the nation and humanity. We conduct research, provide education, and deliver community services by enhancing knowledge that benefits the community, the nation, and the world. We have been learning from one another and get stronger together since we believe that knowledge is not useful unless it is shared with others. The learning process will never cease developing. At UGM, we learn by continuously exploring sciences, learning from history, observing the present, and researching for the future. We always work hard and never give up. The learning and research processes at UGM continue to run together and explore state-of-the-art innovations. To create a convenient, environmentally friendly, and pollution-free green campus, UGM has built a wisdom park that substantiates the teaching and learning process. The park per se is open to the public. UGM has also developed drinking water facilities throughout the campus, provided by a drinking water supporting unit. This system is harnessed by the entire academic community of UGM. As the manifestation of its teaching endeavor, UGM operates various field laboratories for educational and research purposes. Furthermore, UGM has established and run a science technopark as an embodiment of its capability of
His Excellency, the Minister of State-Owned Enterprises, Mr. Ict-Pep, His Excellency, Representative of the Minister of Education, Culture, Research and Technology, Professor Insinyur Nizam, MSc, DIC, PhD, IPU, ASEAN Engineering, the Honorable President Director of PLN, Insinyur Zulkifli Zaini, MBA, the Honorable Rector of Universitas Gadjah Mada, Professor Insinyur Panut Mulyono, Master of Engineering, Doctor of Engineering, IPU, ASEAN Engineering, IEEE Indonesia, Dr. Linawati, GM PLN Puslitbang, Insinyur Iswan Prahastono, MPhil. all speakers, moderators, distinguished guests, and participants. Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera untuk kita semua. Shalom, Om Swastiastu, Namo Buddhaya, Salam Kebajikan. Welcome to the 3rd International Conference on Technology and Policy in Electric Power and Energy, Emerging Energy Sustainability, Smart Grid, and Microgrid Technologies for Future Power System. Ladies and gentlemen, let us now sing our national anthem, Indonesia Raya. From all around the world, welcome to the 3rd International Conference on Technology and Policy in Electric Power and Energy, ICT-PEP 2021. This conference is held as a series of activities from the National Electricity Day and BUMN Summit. This is the 2nd year, ladies and gentlemen, we are holding this conference virtually despite our pandemic. Although during this conference we can meet each other in person, but hopefully we still can get the best experience from this conference. And I am Santi Zaidan as your Master of Ceremony. It's been a very great honor for me to be able to say hi and greet everyone this morning. We are now live from Yogyakarta, Indonesia at 8:30 Indonesia time, GMT +7. I would like to say good afternoon or maybe good evening for ladies and gentlemen or participants who live in other countries. Thank you very much for your support and participation. Ladies and gentlemen, before we proceed to the main agenda this morning, for the successful event today, let us begin with praying together according to our respective religions. Pray begin. Pray and. Distinguished guests, ladies and gentlemen, clean energy and smart grid are key components to ensure energy sustainability. However, there are some issues related to technology and policy readiness in this area. This conference, ladies and gentlemen, is a platform for policymakers from governments, researchers from national and international energy research institutes, academicians from universities, as well as managers and engineers from the industry to share the ideas and research results that are related to these issues. And to begin this conference, ladies and gentlemen, we would like to first invite ICT-PEP 2021 Chair, Mr. Sargia, PhD. The screen is yours now.
Okay, thank you very much. Assalamualaikum warahmatullahi wabarakatuh. Very good morning, Excellencies, distinguished guests, ladies and gentlemen. Selamat pagi, salam sejahtera, dan salam sehat untuk kita semuanya. Excellency Minister of State-Owned Enterprises, who is represented by Mr. Susianto, the Secretary of the Ministry. Excellency Minister of Education, Culture, Research and Technology, who is represented by Professor Nizam, the Director General of Higher Education. Excellency President Director of PT-PLN, Bapak Insinyur Zulkifli Jani, MBA. Excellency all of POD members of PT-PLN. Excellency General Manager of PT-PLN Puslipang Research and Development, Bapak Iswan Prastono. Excellency Rector of Universitas Gadjah Mada, Profesor Pandut Mulyono. Distinguished Representative of IEEE Indonesia Section, Ibu Linawati, PhD. Distinguished Chairman of Forum Pendidikan Tinggi Teknik Elektro Indonesia, Profesor Hedi Siono. Distinguished guests, college, researcher, professional, ladies and gentlemen. Welcome to the third International Conference on Technology and Policy in Electric Power and Energy, or ICT-TEP 2021. This year theme is Emerging Energy Sustainability, Smart Grid and Microgrid Technologies for Future Power System. This conference is organized in collaboration between PT-PLN Puslipang Research and Development with the Department of Electrical Engineering, Universitas Gadjah Mada, and then Forum Pendidikan Tinggi Teknik Elektro Indonesia, or FORTE. This is the second year conference. We are holding this conference virtually. Although this condition still hinders us from meeting each other in person, I really hope we can get the best experience from this conference. I could proudly inform you that we have received 207 submissions for ICT-TEP 2021 from researchers and engineers in Indonesia and 20 other countries in the world. Only 80 papers have been selected to be presented at this conference, or an acceptance rate of nearly 40%. The abstract of these accepted papers have been compiled into this book, and the full papers, after being presented by the authors, will then be submitted for inclusion into IEEE Expo. I would like to express my sincere gratitude to all keynote and invited speakers, Mr. Susianto, the Secretary of Ministry, on behalf of Ministry of State-Owned Enterprise, Professor Nizam, the Director General of Higher Education, on behalf of the Minister of Education, Culture, Research and Technology, Professor Edward Mulyadi from Auburn University, USA, Professor Joseph Guerrero from Aalborg University, Denmark, Professor Andrew Beckers from Australian National University, Professor Sanjeev Kumar Panda from National University of Singapore, and Professor Angus Kos from the Neo-Stia University, India, for sharing their knowledge and experience in this conference. I would like to extend my sincere appreciation to IEEE Indonesia Section and IEEE Power and Energy Society Indonesia Chapter for their continued support. Thank you for Forum Pendidikan Tinggi Teknik Indonesia, or Indonesian Electrical Engineering Higher Education Forum, FORTE, for their inputs on the conference technical track. I also would like to thank all the chairperson and the committee members who have been working hard to succeed in this conference. Finally, I would like to thank all the authors, presenters, reviewers, and participants for their contribution to ICT-TEP 2021. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.
Okay, thank you, Mr. Sarjia, PhD, for delivering the first opening speech. Thank you very much, Prof. The next opening speech, ladies and gentlemen, will be delivered by General Manager of PLN Puslipang, Insinyur Iswan Prahastono, MPhil. This place is yours.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Om Swastiastu, Namo Buddhaya, Salam Kebajikan, Good progress to all of us. Distinguished Representative Minister of Indonesian State-Owned Company Coordinator, BUMN, Distinguished Representative Minister of Education, Culture, Research, and Technology, Distinguished Direktur Utama, Mr. Zulkifli Zaini, and Board of Director of PT PLN Persero, Distinguished Chairman of IEEE Indonesian Section, Distinguished Rector of Universitas Gadjah Mada Indonesia, Mr. Panut Mulyono, distinguished guests, colleagues, researchers, professionals, ladies and gentlemen. It's a great honor for me to welcome you to the third International Conference on Technology and Policy in Electric Power and Energy, ICT-PEP 2021. Like last year, ICT-PEP 2021 is held virtually due to the COVID-19 pandemic. The submitted paper increased 30% compared to the last year. This means that COVID-19 is not a barrier anymore for engineers and researchers to share their knowledge and experience. We have received 207 papers from 21 countries, and only 39% of papers have been accepted and will be presented today and tomorrow. For your information, this event, this international conference, ICT-PEP, will be held by PLN annually every year. For this success, I would like to express my gratitude to the Power System and Renewable Energy Integration Research Group at Fakulty of Engineering Universitas Gadjah Mada for coordinating and organizing this conference with us. Strong appreciation to IEEE Indonesian Section and IEEE Power and Energy Society chapter, so that the ICT-PEP 2021 quality could be improved and maintained in the international coverage. Thank you also to the chairs, committee members, reviewers, and invited speaker of ICT-PEP 2021 for making a tremendous contribution to this conference. Above all, thank all of you for your participating this conference. I hope you enjoy and could mutually benefiting from this virtual ICT-PEP conference. Wassalamualaikum warahmatullahi wabarakatuh. Namo Buddhaya, good purpose to all of us. Om Santi, Santi, Santi Om.
Thank you, Engineer Iswan Prahastono MPhil, for delivering the second opening speech this morning. Next, the opening speech will be delivered by IEEE Indonesia, Dr. Linawati.
Okay, thank you for everyone. Dear distinguished guests, colleagues, researchers, professionals, ladies and gentlemen, good morning, warm and spirited greeting. First of all, let me thanks to the Honorable Rector of Universitas Gadjah Mada, Professor Panut Mulyono, President Director of PLN, Insinyur Zulkifli Zaini MBA, General Manager PLN Puslitbang Research Center, Insinyur Iswan Prahastono, and Dr. Sarjia as General Chair of this conference, for inviting me to give a few words at the opening of this conference. Honorable Minister of Education, Culture, Research and Technology, Minister of State-Owned Enterprise or BUMN, Professor Edward Mulyadi from Auburn University, Professor Joseph Jurero from Albert University, Professor Andrew Blacker from Australian National University, Dr. Sanip Kumar Panda, National University of Singapore, and Dr. Ankus Ghosh from Nyotia University, India, as a keynote and invited speakers, as well presenter and participant the 2021 International Conference on Technology and Policy in Energy and Electric Power. As Secretary of the IEEE Indonesia section and on behalf of the IEEE Indonesia section chair, I'm glad to warm welcome you to the ICT PFP 2021. Due to this year's pandemic situation, the conference is held as a completely virtual conference. I also want to thank all of you who joined this conference. I believe that this event activity can enrich our knowledge about the latest issue, opinion, bright ideas for student researcher, professional, and academic. New innovation in technology for a better future are emerging, especially in the field of energy and electric power. The collaboration between universities, industry, and government, and also professional, is very important in creating jobs and developing civilization. Honorable guests, speakers, ladies and gentlemen, IEEE Indonesia as a regional organizational unit of IEEE was founded in 1988, and its development over the past 33 years, IEEE Indonesia has contributed significantly in various activities that encourage the role of science and technology for humanity in Indonesia. And we, together with volunteers, members, and all stakeholders, has produced various activities by supporting more than 20,000 IEEE conference publications and more than 260 IEEE journal publications by Indonesian authors since 1988. From this data, we still need to encourage the growth of publication from Indonesian authors in high-quality IEEE journal. IEEE Indonesia has also sponsored and supported more than 50 high-quality conferences each year, including this conference. The result of the quality conference publication are published in the IEEE Explore Digital Library, indexed by Scopus, WS, and other major databases, which have more than 5 million publications and more than 12 million downloads each month. As we all know, IEEE always maintains high-quality publication as part of the intellectual culture. IEEE Indonesia also holds more than 40 professional, technical, non-technical, and administrative activities each year for all its members. Currently, we have more than 2,000 members and more than 50 senior members consist of professional, industry, academia, and government. The IEEE Indonesia has also supported the development of 26 technical society chapters or joint chapters, including power society chapters, a forum for technical activities for Indonesia members. IEEE Indonesia has also supported the development of 26 university student grants and 9 IEEE student grants. We have a non-technical affinity group, consists of young professional and a woman in engineering and one IEEE science on e-health and telemedicine interest group. IEEE Indonesia also encourage and support the birth of subsection in Eastern and Western Indonesia so that members throughout Indonesia can feel the closeness and great benefit of their membership in IEEE activities. Hence, I would like to encourage all of you to become an IEEE members to get all the benefit, including broader networking between academia, professional, and government members. IEEE Indonesia also initiated cooperation with the Directorate General of Higher Education in order to synchronize and support IEEE activities in the Indonesian Ministry of Education, Culture, and Research and Technology program, especially to support the Campus Merdeka, Merdeka Belajar, or Emancipated Learning program. IEEE Indonesia is also exploring cooperation with the Indonesian industry in various activities. IEEE Indonesia is also actively involved in providing input in the preparation of related government regulation and other activities. Finally, Putting together a conference is not an easy task. We are grateful to all parties who work together to help us build this exciting conference program. We hope you will join us to make the 2021 International Conference on Technology and Policy in Energy and Electric Power a memorable event, and you will have a productive and enjoyable time at this very special conference. Stay healthy, stay active. Thank you.
Thank you, Dr. Linawati, for delivering the opening speech. The next opening speech, ladies and gentlemen, will be delivered by Rector of Universitas Gadjah Mada, Professor Insinyur Panut Mulyono, Master of Engineering, Doctor of Engineering, IPU, ASEAN Engineering.
Okay, thank you so much. Could you hear me? Okay, thank you so much. Yeah, Excellency Mr. Nadiem Anwar Makarim, Minister for Education, Culture, Research and Technology, who is represented by Professor Nizam, Director General of Higher Education, Research and Technology, Mr. Eric Tauhid, Minister for State-Owned Enterprises, or his representative, Distinguished Insinyur Zulkifli Zaini, MBA, President Director of PLN, Distinguished Insinyur Iswan Prahastono, MPhil, GM, PLN Puslitbang, Distinguished Dr. Linawati, Secretary of IEEE Indonesia, of course my colleague, Distinguished Dr. Wasis Bilda, Dean of the Faculty of Engineering, Universitas Gadjah Mada, Honorable Dr. Sarjio and Dr. Roni Irmawan, Head of Steering Committee and Head of Organizing Committee of the Third International Conference on Technology and Policy in Electrical Power and Energy, Professor Edward Mulyadi, Auburn University, USA, Professor Joseph Guerrero, Albert University, Denmark, Professor Andrew Blakers, Australian National University, Dr. Sanjeev Kumar Panda, National University of Singapore, Dr. Ankush Kos, the Newtia University, India, and of course, honorable committee members, speakers, participants, and partners. Ladies and gentlemen, good morning, good afternoon, good evening. Assalamualaikum warahmatullahi wabarakatuh. May peace be upon all of us. On behalf of Universitas Gadjah Mada, it is my pleasure and privilege to welcome you all to Jakarta virtually for the Third International Conference on Technology and Policy in Electric Power and Energy, ICT, PEP 2021, with the theme of Emerging Energy Sustainability, Smart Grid, and Microgrid Technologies for Future Power System, organized by the State Electricity Enterprises, PT PLN, in collaboration with the Faculty of Engineering, Universitas Gadjah Mada. In this opportunity, I would like to extend my gratitude to the State Electricity Enterprise and Faculty of Engineering, all UGM partners, distinguished keynote speakers, invited speakers, presenters, participants, and committee of the conference. It is unfortunate that we have to conduct this conference virtually due to the global pandemic of COVID-19. But I'm sure, however, this will not weaken the meaning of this conference. While we are sad that we cannot see each other in person, it is undeniable how this global pandemic has provided us with opportunities and new insights of doing things. Excellencies, ladies and gentlemen, clean energy and smart grid are key components to ensure energy sustainability. To provision of adequate, reliable, and affordable energy in conformity with social and environmental requirements. Our environment is now suffering due to exploitation of natural resources by human beings. The two most important environmental hazards faced by the humankind today are air pollution and global warming. Both have a direct link with our current overdependence on fossil fuel. So renewable energy, smart grid, and microgrid technology is very, very important. Excellencies, ladies and gentlemen, I do hope that this conference will be the media to discuss and collect some information about the present and trend of research and development in the field of energy sustainability, smart grid, and microgrid technologies for future power system to contribute in solving world environmental problem. In this conference, academia, researcher, manager, engineer, and policymaker will have the opportunity to gain precious insight into the future of science and technology. I firmly believe that ICT PEP 2021 will contribute to the recent advancement of science and technology for sustainable development of human civilization. Moreover, this intellectual gathering will be a great encouragement for the science and technology innovation, which will eventually contribute to the sustainable development of quality life. Lastly, I am deeply grateful to the keynote and invited speakers, participants, sponsoring organizations, and members of the organizing committee to make this conference remarkable, successful. The true materialization of the research ideas presented in this international conference will contribute to the global science and technological advancement. I'm expecting this conference will also provide us better linkage, friendship, and collaboration. I wish you all enjoy a wonderful and fruitful conference. Thank you very much. God bless us. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you, Prof. Professor Insinyur Panut Mulyono, Master of Engineering, Doctor of Engineering, IPU ASEAN Engineering, for delivering the opening speech. And the next one, ladies and gentlemen, we also will hear an opening speech that will be delivered by President Director of PLN Indonesia, Insinyur Zulkifli Zaini, MBA, who will also officially open this conference today.
Terima kasih. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh.
Assalamualaikum warahmatullahi wabarakatuh.
Om Swastiastu, Namo Buddhaya, Salam Kebajikan. Distinguished Director General of Higher Education, Ministry of Education and Culture, Republic of Indonesia, Professor Nizam, Distinguished Chairman of IEEE Indonesia Section, Dr. In Wahyudi Hasbi, Distinguished Rector of Universitas Gadjah Mada, Professor Panut Mulyono, invited speakers, Professor Edward Mulyadi from Auburn University, US, Professor Joseph Vereto from Aalborg University, Denmark, Professor Andrew Blakers from Australian National University, Dr. Sanjeev Kumar Manda from National University Singapore, Dr. Ankush Ghosh from Neosia University India, the representative from the Ministry of State-Owned Enterprises, distinguished Board of Directors of PTPLN, all seniors leaders of PLN, and of course, all participants of ICT PEP 2021. Distinguished guests, ladies and gentlemen, it's a true pleasure for me to welcome you all to the third International Conference on Technology and Policy in Electric Power Energy, ICT PEP 2021. This year is the second time we are holding this conference online. We are continuing our success of holding this conference, that is, by attracting the audience from at least 20 countries. The ICT-PEP is one of the international conferences organized in Indonesia that has had a strong reputation in recent years. The previous conferences, the first ICT-PEP 2019 and the second ICT-PEP 2020 were successfully held with more than 500 participants, reflecting the whole-wide expert on the future power system and related technology from different continents, including Asia, Europe, America, Africa, Australia, and surely this is a proof of the quality of ICT-PEP as a melting pot between engineers and researchers to broaden their knowledge by learning from others. Continuing the success of our previous conferences, ICT-PEP 2021 is created with the belief that clean energy and smart grid are key components to ensure energy sustainability and the future development of this technology start with grid collaboration. This conference is a platform for government, policymakers, researchers from national and international energy research institutes, academics from universities, and managers, engineers from the industry to share ideas and research results related to these issues. In this conference, a specific discussion on artificial intelligence and cyber security will also be conducted. Therefore, this conference is presented with the theme Emerging Energy Sustainability, Smart Grid, and MICROGRID technology for the future power system. This conference brings benefit not only to researchers but also to industry and government. Researchers could expand their knowledge and present their ideas in the scope of advanced and intelligent smart grid. Together with electrical industry participants and the Indonesian government, grid collaboration could be achieved. Additionally, as the Indonesian Electric State-Owned Company, PTPLN Persero, will get imperative information on the latest technology in the field of power system modernization and a comprehensive knowledge where the trend will go to adopt to them in the future. As a result, an opportunity for participants to establish a triple health network between researchers, industry, and government could be substantially realized. PTPLN Persero is currently working to use or even convert our existing fossil power plant with more sustainable power resources. Here, PTPLN Research Institute as one of our strategic unit, plays an important role in solving these challenges and suggesting new ideas. I'm gratefully to inform that PTPN Persero keeping this conference as annual event. I also appreciate the help of the power system and renewable energy integration PSR EI Research Group at the Faculty of Engineering, Universitas Gadjah Mada, in organizing this event together with us in PLN. Furthermore, to keep the quality of the conference at an international level, I also appreciate the help of IEEE Indonesia section and IEEE Power Energy Society PS chapter. Last but not least, I would like to express my sincere gratitude to the speakers, Director General of Higher Education, Ministry of Education and Culture, Republic of Indonesia, Professor Nizam, Professor Edward Mulyadi, Professor Joseph Guerrero, Professor Andre Blakers, Dr. Sanjeev Kumar Panda, Dr. Ankus Ghosh, for sharing their knowledge and experience in this conference. I would like to thank all the chairs and committee members for their hard work to the success of this conference. Last but not least, I would like to thank all the presenters, authors, and participants of this conference. I wish you all a great conference. Wabillahi taufiq wal hidayah. Wassalamualaikum warahmatullahi wabarakatuh.
Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Welcome to ICT AEP 2021.
Thank you very much, Engineer Zulkifli Zaini, MBA, for delivering the speech and also open this conference. So, ladies and gentlemen, we are now proceeding to our main agenda, that is keynote speech. I would like to invite our keynote speakers, also representing Minister of Education, Culture, Research and Technology, Professor Insinyur Nizam, MSc, ICT PhD, IPU, ASEAN Engineering.
Assalamualaikum warahmatullahi wabarakatuh. Good morning to all of you. Selamat pagi, salam sehat, salam sejahtera untuk kita semua. Excellency Minister of State Companies, Bapak Erick Thohir, Excellency Rector of Universitas Gadjah Mada, Pak Profesor Panut Mulyono, Excellency President Director of PLN, Bapak Sir Zulkifli Zaini, distinguished speakers, colleagues from IEEE, and participants, ladies and gentlemen. It's a great honor for me to greet you and welcome you in this international conference on energy sustainability, smart grid, and microgrid technologies for future power system. I also would like to congratulate PM and PTPLN for hosting this timely conference. You all know that energy is key to our development. Therefore, this conference on energy is very important. Today, we are facing the global challenge of climate change. There is no other option than to move toward the cleaner energy sources. Sustainability of this planet very much depends on our ability to transform our energy source from non-renewable to renewable energy sources. In addition to improving efficiency and reducing consumption, to achieve all that goals, smart grid and microgrid technology is a must to develop. Please allow me to share screen to share with you the current status as well as research and development and the role of university in achieving more sustainable energy future. Currently, the level of consumption of energy, we can see from this chart that 38% usage of energy consumption is for industry and 40% for transportation. So these are the two major areas of energy consumption in addition to households consumption. And to fulfill that needs, then the source of energy on this right-hand side, we see that significant amount come from non-renewable sources, from oil, gas, and coal, in addition to the LPG, biogas, and biomass. The renewable source of energy is still relatively small compared to the non-renewable sources. This is the projection of the demand for energy to the next 30 years, and the energy mix that is expected to be achieved by 2050. Perhaps this graph better show that. Currently, the percentage of renewable energy is still in the order of 11-12% of the total energy sources, while the target by 2050, 31% of the energy source should come from renewable energy. So this way, this is quite an optimistic target that is hard to achieve but not impossible, although it is still far from the target what we achieve currently. So therefore, research and development in university is very important. The focus for research in renewable energy and new energy sources is focused on four aspects. One is the technology to substitute the existing fuel consumption, and second, on the power generations, research on power generations, especially based on the renewable energy sources, and conversion of energy, the third topic, and fourth, on the sustainability and diversification of energy. So energy sovereignty and diversification of energy sources. These are the four main area of research with regard to new and renewable energy based on the Rencana Induk Riset Nasional 2017-2045. There are already many initiatives coming from universities as well as collaboration between universities and research centers and industry. For instance, in Institute Teknologi Sumatera, they developed the solar power plant fields with about 1 megawatt as an experimental sustainable energy source from campus. And this ITERA collaboration with SUN and MICA, we want to replicate this into as many university as possible. So we have a discussion with WICA, with PLN, with Pertamina, and many other players in solar panel energy to make our universities, our campuses to become more greener. So to make renewable energy as the main source of energy in our campuses. So I hope UTM will be one of those campus to use solar panel, whether rooftop or ground-based. And also in the development of pembangkit listrik panas bumi, geothermal, in Lahindong, there's also collaboration between Pertamina, BPPT, UGM. So we use the development of renewable energy as part of the area of research, as well as join in collaborations with industries to develop the green energy sources. And PLTP Kamojang and also PLT Bayu Sidrap, we hope that those renewable energy development can be part of the research centers, can be part of the research object for our universities. And on hybrid power plants, there are research centers in Baron, the south of Yogyakarta. This is the mix between solar panel, wind power, and diesel power into a hybrid system in Baron. This is Taman Energi Baron in Jakarta. This is in cooperation between BPPT, GM, and LAPAN. And research on ocean power, this has been going on for quite some years, decades even. So we started in the early 90s or late 90s with wave power, tidal power, as well as any other ocean sources of energy. And on biofuel and biomass, I think there's also quite active research in university, like in microalgae biorefinery, on biofuel, on Jatropha, and on the biomass through pellet. And of course, when you talk about renewable energy, then storage is also something of importance. And research in university now has come into like pilot plant and factory, like the lithium battery development in UNS, in cooperation with Pertamina, and also electric vehicle is something that we are accelerating to be developed in cooperation between universities and industrial partners. And at UGM, I also noticed the recycle and recovery of lithium battery. I think this is also the future of sustainable energy future. And smart grid, this is also an area that we would like to accelerate further. And also a cleaner nuclear plant. I think this is something that we should also look at. We also promote our university to become greener through UI Green Metric, in which this is the ranking of universities based on their performance in saving energy, in having cleaner source of energy, water, and conserving water and waste management. These are very good metrics developed by Universitas Indonesia and now globally accepted. And also the impact ranking from Times Education is also we are quite happy with the results. 4 of our universities come into top 100 in university impact rankings of Times Education group. And this, the Gerakan Kampus Mandiri Energy, we would like to accelerate and promote our campuses to become self-sustained in energy by using all the capacity, all the available potential in every university to become part of the national energy mix. So as I mentioned earlier, with several industries, we are in discussion also with the Kementerian SDM to make our campuses cleaner by putting solar panel on ground or rooftop. So I think that is my short presentations on the role of university in accelerating the energy mix and to make a better future, more sustainable energy in the future. And of course, research in smart grid, microgrids is very important to make sure that the plan for more sustainable energy in the future can be implemented well. And thank you very much. Wassalamualaikum warahmatullahi wabarakatuh. Shalom. Good afternoon.
Thank you very much, Professor Insinyur Nizam, for delivering the keynote speech. Distinguished guests, ladies and gentlemen, we are now going to have a very fruitful and great discussion, and we're going to have our moderator to lead the session. I would like to read the CV for our moderator, Mr. Roni Irnawan, STMSC, PhD, SME, Triple E. Mr. Roni Irnawan, STMSC, PhD, is a lecturer of electrical engineering from Gajah Mada University. His main research interests are in HVDC system, power system modeling, power system stability, and wind energy integration. He achieved his bachelor degree in electrical engineering from Gajah Mada University and received a Master of Science in Electric Power Systems from Karmals Technical Hospital, Sweden. Also received a doctoral degree in Electric Power System from Albert University, Denmark. Inviting once again our moderator this morning, Mr. Roni Irnawan, ST, MSc, PhD.
Yeah, thank you very much for your kind introduction. So, good morning, everyone. Distinguished Minister of Education, Culture, Research and Technology, distinguished Rector of Universitas Gajah Mada, UGM, distinguished Minister of BUMN, distinguished Board of Director of Ict-Pep Persero, distinguished Secretary of Indonesian IEEE Indonesian Section, and also distinguished ladies and gentlemen. So yeah, today I will be the moderator for invited speaker. This is the first session for the invited speaker. We will have another session tomorrow morning. And for today's speech, we will have three speakers. The first one will be Professor Edward Mulyadi from Auburn University, US. Second one will be Prof. Joseph Guerrero from Auburn University, Denmark. And the last one, Professor Andrew Blackers, but he won't join us. So this speech will be delivered by Professor Matthew Stokes from Australian National University, Australia. Yeah, so in this year's theme of the third ICT PDP 2021 is regarding emerging energy sustainability, smart grid, and microgrid technologies for future power systems. So we are really glad that these three professors are agreed to give a speech in this session because, as you know, Professor Edward Mulyadi he has background on wind and renewable energy back in the US, and Prof. Joseph from Denmark, he also the leader or the expert for the microgrid system, and Professor Matt Stokes from Australia that also he is an expert as well in renewable energy integration. So for the first speaker, I guess we have Prof. Ed in here. Prof. Ed, are you here? Yeah, he will not deliver the speech by himself. He already recorded his speech. And if you would like to have some question, you can type in your question in the Q&A on there in the Zoom. You can do that, and probably Prof. Ed will directly answer that, or we can do that after playing this game. So the first one will be Prof. Edward Mulyadi. Currently, he's the James J. Danaher Distinguished Professor at the Electrical and Computer Engineering Department, Auburn University, Alabama, US. He joined Auburn University in 2018. Before he joined Auburn University, he was with the National Renewable Energy Laboratory in Colorado, in which he spent like 25 years over there. So he has many patents regarding the wind and also power renewable energy. He also has has more than 300 peer-reviewed journal and conference publication. He has H index of 54 and I-10 index of 176. So without further ado, let's hear our first presenter, Professor Edward Mulyadi.
Good morning, ladies and gentlemen. This is an honor for me to give presentations on marine technologies for electrical power generation. My name is Ed Mulyadi. I'm a professor at Auburn University, and I want to present this presentation on marine technologies. So, as a background, marine hydrokinetics has gained great interest in recent years because its potential to provide a significant contribution to electricity supply around the world. Now, in theory, the total magnitude of the resources on the order of the U.S. electricity demand in the U.S. alone. So, in particular, the U.S. West Coast, Hawaii, and Alaska, they have a lot of wave resources that are among the strongest. Now, the data taken at water depth at 200 meters, this is the year was the studies conducted in 2012. The U.S. electricity generations from this ocean energy or marine hydrokinetic estimated to be 54 terawatt hour per year. So this is very significant. Now let's take a look at the map. This is the map of the U.S. map, and there's the resources along the coast, as you can see. The color here, the ocean wave, is colored blue, including the numbers representing the ocean wave. Now, the ocean current is designated as red color, and then tidal current is the color is green, and river currents is gray. So, as you can see, there are a lot of wave energy around in Hawaii and along the coast, east coast and west coast. And then tidal current is in green. These are the locations that available tidal currents. Also in Alaska, we have a lot of tidal currents as well. Now, this number here, it shows that along the west coast, there are approximately 590 wave energy resource that can be harvested. And then there is about 8 terawatt hour per year for tidal current. And on the east coast side, 240 terawatt hour per year for wave energy and 21 river or tidal currents terawatt hour per year. Now, the ocean current here, it can be found in south of Florida. So this is about 200 terawatt hour per year. And along the Alaskan coast, we have wave energy resource at 1570 terawatt hour per year, and then 416 tidal current resources. This is in terawatt hour per year. So if we tabulated this one here, you can see that total resource in terawatt hour per year, ocean wave, the total is 2640, and ocean current, which is red, is 200 terawatt hour per year, and tidal currents 445, and river currents is 1381. So from all of these here, you can see that their significant amount is even more than 100%, as you can see from here, that marine hydrokinetics can provide to supply U.S. demand. So U.S. demand is around 4,000 terawatt hour per year, and total capacity generations is about 1 terawatt generations. This is all in 2012. Now, in the U.S., a few wave and tidal project has been successfully deployed and tested. This is in 2020, with others progressing with preparation for open testing. So, notably, this is from ORPC that deployed 35 kilowatt RIFGen. This is river generators. This is tested in Alaska. And then Ferdinand Power deployed new turbine. This is in East River near New York City. And there's 3 wave energy developers. They are now prepared for deployment at the U.S. Navy Wave Energy Test Site in Hawaii. First one is 100 kilowatt Triton C. This is from Oscilla Power. And Ocean Energy 500 kilowatt oscillating water column OWC prototype, and then 2 devices from Sea Power. It's called Stingray for power larger than 500 kilowatt applications, and then Sea Ray. This is for small application 1 to 5 kilowatt. Now this is a list of test site. So this is the name of test site. This is in the U.S. This is the location of the test site. There are a lot of test sites in the West Coast. This is Newport, Oregon, Seattle, Washington, and this is in Nenana, Alaska. So it has its own name. You can see that Pacific Marine. So it shows that this is along the West Coast, Pacific Ocean. And then there's East Coast in Jeanette here, North Carolina. This is another wave energy test facility. And there's another one in North Carolina, is in a place called Duck. This is from U.S. Army Corps of Engineers testing facility. And then on the it's a continuation here, there's one in Durham, New Hampshire. This is Center for Open Renewable Energy. And then also in Maine, this is, it looks like it's connected to University of Maine. And the same one here, Deepwater Offshore Renewable Test Site. This is also in Maine. And there's one in Texas. So this is a OTEC test site in Hawaii. And then there is one in Massachusetts, and then there's another one in Florida. So this is all the sites dedicated for marine hydrokinetic or marine technologies. So there are plenty of places that people can choose, and they can perform the test, especially for specific requirements. So it is very important that the test site will match the device that you want to test. So the next one here, I just want to show the global resources of marine hydrokinetics. So as you can see, most of the ocean energy, probably most of the ocean energy came from wave energy. So because wave energy, you can find or you can deploy wave energy converters is almost in any place, while ocean current normally is kind of the resources is very specific. So as you can see from here, this is Indonesia on the right hand side in the middle. This is, as you can see, the map of Indonesia. So there's significant resources, because you can see here 20. Now, if you compare to the United States, they are almost the same in the sense that this is around 20 in Alaska, this is a little bit higher, 30, and then, even going up north, is even better for the wave energy. But in Indonesia itself, there are plenty of resource for ocean energy here. Now, let me continue to the next one. So marine hydrokinetic technologies is still emerging. So this is there are a lot of different types of wave energy converters, WEC, and then also CEC, which is current energy converter. So the designs, there's many types and many prototypes that they proposed. And like any other new technologies, what happens is that a lot of competing technologies, but eventually what will be successful is whoever can build a stronger, sturdy, high efficiency machines at affordable cost. I think that's the key point. So from so many different designs, eventually it will merge to the so-called winning design, and that will be decided by market, of course. So we are developing these prototypes right now, and hopefully within 5 to 10 years, probably we have a lot of wave energy converters and current energy converters installed, all over the world. So a table to compare different marine hydrokinetic technology in terms of their complexity, performance, reliability can be found. Unfortunately, is mentioned here that marine hydrokinetic devices and technology are very broad and are not ready to be disseminated to the general public. So it's not ready for market yet. So eventually the winning concept will reach the market, and it will will reach its maturity, just like the way the wind industry developed. In the beginning, when the wind industry just started, so there are a lot of options, there are a lot of designs. Then eventually they merge into horizontal axis machines, and so once they found a good design, then normally there will be big manufacturers that will manufactures that concept. So wave energy conversion devices extract energy contained within ocean surface waves and convert it to useful electrical power. So like other renewable energy, basically the source is the sun, right? The solar. Solar created wind, and wind blow, on the surface of the ocean, and then that creates a wave, and that we can harvest the energy contained in the wave. And as you can see here, there are 100 prototypes of various wave energy converters in the systems. These devices are typically divided into oscillating types, and then there's the so-called oscillating water column, and another one called overtopping design. Now, oscillating type of wave energy design, converter design here consists of one body or multiple bodies that are designed to directly convert wave energy into electrical power from the wave-induced relation, translation motion or rotational motions within the body and a reference frame. Now, of course, there are two types. One is using linear motion or linear generator. The other one using rotary generators. Now, this is an example of a buoy system. This is also called point absorber. So a point absorber is basically a floating structure which absorbs energy from all directions through its movement at or near the water surface. So when this float here moving up and down, so this is called the translator. The other one is the stator, right? So normally the winding is located at the stator, and the float here will consist of either like permanent magnets or a field winding that created a flux. And the motion of movement of this float here will make the flux travel up and down and crossing the windings on the stationary center. Now, so when the wave moving upward, the float is moving up. When the wave moving downward, the float also moving downward here. Now, of course, there's a cable mooring here, and also the electrical output here can travel, along this cable mooring. This is very important because wave is unpredictable, and you do not want to lose your generator and swept by a wave. And this is a typical configuration. Now, another one is called oscillating surge wave energy converters, or OSWEC here, which basically extract energy from wave surges. So this is normally in shallow water, and when the wave moving going to the shore here, it will bring this looks like a window here or door, and then there's hinges here at the bottom, and the movement between this flap here moving back and forth following the wave, then it will be converted into this piston here that will pump the seawater through this flow line here into the so-called accumulator, and then it will be the seawater will be returned here. But meanwhile, this accumulator here will have a lot of pressure that will convert into the used Pelton wheel and the generator inside this housing here, and you eventually will generate electricity that you put into transformer, step-up transformer, and the power will be transmitted over a long distance. So this is a very simple way to describe the oscillating surge wave energy converters. This is another type. It's called floating multi-body pitching device, also called attenuator. So the definition of attenuator is basically a floating device which operates in parallel with the wave direction and effectively rides the wave. So the wave motion is in this direction. You see the arrow, wave direction, and you convert all the generators is in the junction here, and the output power is transmitted to the power cables here that will go to the substations. Now, as an example, there's a Pelamis T1, which is 120 meter long and 3.5 meter diameters. So the first one, this is 750, and then subsequently they build a longer one. This is the concept. Every time it moves horizontally or vertically, they make a motion and they basically generate electricity. Now, this is an oscillating water column that basically this is like a piston, like a bike pump, right? So the surface of water is the piston, and when the waves are moving up like this, then it blow air, or we call it exhale. So you blow air through the turbine here, and it is connected to the generators. Now, the same way, if you inhale or you suck air when the surface of water is going down, when the wave is going down, it also rotates or drives this turbine and the generator subsequently. Now, this is called Wells turbine. This company used for OWC. And this is very unique because when it inhale or exhale, both directions, the rotation of the turbine stays the same, just like this, right? So this is very convenient because it will improve the efficiency of generators. So the rotational speed doesn't have to go to 0 and negative. So it will always continue in the same direction. This is another one. It's called overtopping device, where the motion of wave here is accumulated here, and this is like a funnel, and then there's a hydro turbine there. So this hydro turbine here will be connected to generator, and the water will flow downward, and then it will generate electricity. So very conventional. Now this is the diagram for wave dragon. This is in principle, this is the same way that basically when the kinetic energy of the wave energy here moving up, and then it will turn these generators, and this generator create electricity. So this is just an example from ocean power technologies. This is a power buoy. This is a real system being tested, at sea. This is another type. This is this point absorber developed by Columbia Power Technologies. This is undergoing testing in Puget Sound. This is very interesting, and you can search in the internet. They have a nice system that have 2 wings and the generators in the middle. So this wing here will move up and down to generate electricity from the generator in the middle. This is the oscillating water column. This oscillating water column device showing the air turbine is used to, this is the air turbine. As you can see, the Wells turbine is here. I really like this concept because this concept, the turbine is not directly connected to the wave per se, but it used the air that's being pumped in and out, and it's very convenient that you can actually make it has very high speed rotational speed here by the air going in and out, and as a result you can use smaller generators. So current energy technology is based on current for ocean, tidal, and river currents, and collectively they called current energy converter. And in most places, the dominant constituent is principle based on the moon, right? So the tidal normally change directions every 6 hours, and this is like very predictable. Now, on the other hand, the ocean current refer to like in the Gulf Stream, for example, North Atlantic Ocean, also in North Pacific Ocean as well. There are 2 largest ocean currents here. Now, this technology is significantly more mature than with energy converter because their design draw on decades of research and development experience in the wind energy and shipbuilding industries. So if you look at this, currently under development, this is resemble wind turbines. There's two common types. The first one is conventional axial axis turbines, and then cross flow turbines. So mathematically, the maximum theoretical conversion can reach 59%, but apparently efficiency of 50% has been achieved by prototype devices operating in real life conditions, real world conditions. Now this is horizontal axis machines. So the axial flow turbine current energy converters. This is developed at East River, deployed at East River near New York City. So this is I think this is let me see. This is a 20 kilowatt machines. Now this one here is a cross flow turbine developed by ORPC or Ocean Renewable Power Company, and this is being tested in open water test. Now, in conclusion, with energy converters and current energy converters have the potential to be the major power generation of the future, especially in for Indonesia, because Indonesia consists of 17,000, more than 17,000 islands, and most of the population live near the coast, and so that it doesn't require it doesn't require transmission power, so the output power from with energy farms, for example, or current energy farms, can be used directly with with the population along the coast. Now, so that's why I mentioned that this is probably a very good option for Indonesia, because there are so many islands in Indonesia. So the modular with energy converter make it possible to scale up power generation in stages over the years without major modification to the existing power system network. Right. So it's normally this kind of machines is not a single machine, single big machines, but multiple machines. Just like the way the wind farm is, they have so many turbines within wind farms. The same thing with the marine hydrokinetics. It's not single generator, but it's multiple generators connected in parallel, and that will produce power that you need. Now, this is the reference. You can take a look at these references and download it. I would suggest that you go to this NREL website, www.nrel/publication.html, and you can search, by topics, by author, and so on. That is all I have, and thank you very much for your attention. Thank you. Bye-bye.
Yeah, thank you very much, Prof. Ed, for your presentation. I don't know if Prof. Ed still joining us today.
Yeah, good morning.
Good evening.
Good morning. Yes. There's 12 hours difference here.
Yeah.
If there is any questions, please let me know, and I'll try to answer.
Yes. So to the audience, if you have any question, you can type in into the Q&A and see, and we can just direct it ask to Prof. Ed to answer it. Maybe while we're waiting for the question, I would like to ask something, Prof. Ed. There are, in your presentation, you show a lot of technology regarding the wind energy, with generators, and then current energy converter. But as you said before, it's not yet commercialized. What is hindering that? Because the potential is there, the technology is there, but why it's not in the market yet? Do you have any?
Yeah. That's very good questions actually. Because there's a big difference between wind turbine and wave energy or ocean energy. In the sense that the water density is like 1,000 times higher than air. So wind is like you call it in Indonesian angin sepoi-sepoi, right? But if you have wave, that's very heavy, very rough. It's the environment itself. When the wave hit the turbine, it's just like it just the impact is very high. So mechanical design is probably the challenge. How to design a structure that's sturdy. In addition to that, you get an environment that's like salty, a lot of corrosion. So it's a big challenge, But that's how good for the engineers, because engineers like challenge, right? Yeah. So I think we will have some few years, and I believe that I think Indonesian engineers can contribute to the technology. In particular, because they're everywhere is ocean. You drive few kilometers. In fact, if you I think the Laut Selatan Jawa, there's like Java Sea, Laut Java. I think that I think there's a lot of potential. You can see that the wave is very high, right? I guess because Nyai Roro Kidul maybe that's like the queen of the ocean, right? So there are a lot of potential, especially probably UGM for Gamma. That will be a lot of potential to do research in this area. Yeah.
Oh, thank you very much.
You're welcome.
Yeah. But I guess the future is bright, right? So it will come, right? It will come. Just like when it started slowly, like a few watts and then kilowatts, and now it's reaching 15, 16 megawatts, right?
Yeah. So we'll be happy to help, and we can make connection with NREL as well. And I remember that Pak Sarjia and Pak Ramawan visited NREL when I was there, and they also visited me when I'm in Auburn University. So it's very nice. Yeah. Okay, looking forward for any collaborations within your university and also with PLN.
So we have a question from Mr. Edward Sitorus, mistaken to pronounce the name. How about the price in terms of kilowatt per dollar or the energy price for the since right now it's still in a development phase? Still fairly high, or
right now it's it's very high. People can quote any numbers, but if you really order this product, this unit, it's going to be very costly. I do not have the number in my hand, but if you go to a report from IEA, from IRENA, or DOE, I'm sure that you will have a number, but it's difficult to compare with wind and PV because it's mature technology. It's always like that. Most of the development right now is the prototype, and hopefully, once they find the circuit recipes, hopefully they can build it very cheap. Yeah, so we just wait for Indonesian engineer here to invent something that is affordable.
Thank you. Another question from the general manager of PLN Puslitan.
Okay, yeah.
So is it possible to make the wind generator or CEC mobile or floating design, or we need to have a strong structure for that?
No. Well, you need to have an anchor. a lot of wave generations. There's many different applications. For example, at this point, people are comfortable building with energy for sensors. For measuring wind, measuring temperature, measuring the wave. So weather-related kind of sensors that will broadcast, the signals to the satellite, and you receive the data. But there's a serious attempt, for building this technology for people for example, in Alaska, they have a lot of resources, and a lot of places they do not have a good electrical network. Yeah, so obviously, it's very easy because you can pull it by a ship, right? I mean, to destinations. You don't even need to go through the road, right? Right now, wind turbines is kind of limited in size, because the bigger the size, then you cannot transport. The transport is very difficult. So that's why people right now building offshore wind, because the size is a non-issue, because you can ship it, right? So the traffic is not non-issue. Yeah, I'm quite positive that we should be able to get into commercialization within 10 years, or 5 to 10 years.
Yeah, we have another question in relation with the energy price. How about the efficiency?
Oh, efficiency is very good.
PV or wind?
Efficiency is very good, actually. If you spread your hand like this, both hands, right? This like you got a 30 kilowatt per meter. 30 kilowatt per meter. That's huge, right? so that's why, if we can build an equipment that is sturdy enough, flexible enough, that is able to take the wave forces and convert it into electricity, that's the key solutions. Because the energy content itself, just like 30 kilowatt per meter, it's huge, right? Yeah, big difference.
How about the variability, or is there any intermittent?
For wave energy, similar to wind in the sense that in winter, the wave is normally rougher. Is going. There are more wave and higher wave, and during summer it's normally quiet, very quiet. Now, on the other hand, tidal energy is very consistent. It changes every 6 hours, in and out, in and out, right? So it is very predictable. I do not know in Indonesia what is the tidal potential, but I'm sure there are a lot of places tidal, because the concept of the turbine itself, the concept is very similar whether you put it as a tidal or for river current. If you go to Kalimantan, Borneo, right, there's Mahakam, there's huge river. And even in Sumatra, there are a lot of rivers that I think there are a lot of potential there. And in particular, this river is kind of long, and most people like to live by the river, right? Because there's a water resource, right? This sort of living, right? Water. So in terms of electrical generations, you do not need transmission line, because you generate there, you use it over there, and wire size is very easy. It's not like transmission line kilovolt. So yeah. So it just Indonesia have everything. Right, you live in tropical. There are a lot of rain, and you get a lot of mountains, right? Dr. Professor Matthew Stock will talk about the mapping, and I read his article that Indonesia have enough potential for pump storage hydro. for 100% renewable, maybe more than 100%. So I'm really impressed by the work by Professor Stokes and his team, mapping the entire world, and looking at the potential of pump storage hydro. Yeah, I just so happen to have a lot of projects on adjustable speed pump storage hydro, and so this is something that kind of a dream, because pump storage hydro is like the cheapest battery available. If you have the resource there, then you better use it, right? So there's a lot of potential to balance variability of renewable energy. Yeah.
Yeah, great. Thank you very much. That was the question from Pak Rusnanto from DGM.
Oh, okay. Rusnanto, yeah.
I guess it's a bit late for you right now. So
it's okay.
There will be a lot of questions regarding this topic, and yes.
Yeah, you can send me an email.
Yeah, it's still coming up.
Yeah.
So
Sure.
Maybe I will try to collect them all, and then later on we will try to translate you and see if you can answer some of those. And we will send to the attendee the answer for the question. But yeah, it was really nice discussion, and I don't want to hold you anywhere.
Yeah. Okay, I think
Thank you very much, Professor.
Okay. Thank you.
Looking forward to meeting you again.
Okay.
Yeah.
Thank you. I appreciate all the questions. Thank you for inviting me.
Thank you, Professor.
Right.
So thank you, Professor Edward Mulyadi from Auburn University, Alabama. And we will move to the second presenter, which was already been introduced by Prof. Ed. I would like to invite Prof. Matthew Stokes from Australia National University, Australia. Are you there, Professor?
I'm there. Can you hear me?
Sorry?
Can you hear me?
Yes.
Excellent. So let me share screen.
Yeah, while you are preparing for the screen, I would like to introduce Professor Matthew Stokes here. So Professor Matthew Stokes is the Associate Professor at Australian National University since 2020, and he was the Senior Research Fellow at Australian National University from 2013 and until 2020. He won Eureka Prize for Environmental Science in 2017. He has done a lot of projects, and one of the projects has been mentioned by Prof. Ed. It was the Global Pump Hydro Energy Storage Atlas. It was, I guess it's still ongoing, right? And they have a unique 3D visualization from National Map, which is a platform with over 150,000 users from 130 countries in the world. So it was quite used. Apart from that, we also have done a zero carbon energy for Asia Pacific project, which is become the steering committee, and also advanced surface and contact technology for industrial silicon photovoltaics. So in this, he has also performed consultancies for energy storage studies in New South Wales, Victorian and Queensland governments, and also industry. And and today's presentation, I believe it will be regarding the PV, right?
PV and some pump hydro.
PV and pump hydro. So it will be from the ocean, from what have been presented by Professor Ed. Now we are moving to the PV. Okay. So without further ado, the time is yours, Professor Matthew Stokes.
Okay, thanks very much for the introduction, Roni. So what I'll be talking to you today is around the potential role for solar energy in Indonesia, and also, as Ed very kindly pointed out, the connection through to pumped hydro as a means of supporting generation at other times of the day. So this is work that's been undertaken by the RE100 group here at the Australian National University in Canberra, Australia. And I'd particularly like to note a significant amount of this work was undertaken by David Silalahi, who before coming to commence a PhD with us a couple of years ago had 10 years in the Indonesian Department of Energy and has been an important contributor to the work that I'm presenting today. So why solar? I think one of the things that you can recognise when it comes to solar is that it is now the leading source of new electricity generation capacity worldwide. So there was more solar installed in 2020 than wind, all the other renewables, and considerably more than fossil fuels, gas and coal. And the reason for that is largely due to the very dramatic drops in the price of solar photovoltaics. And in the most recent International Energy Agency's Energy Outlook, they acknowledge that good solar projects are now the cheapest source of electricity in history. And this is due to the very dramatic drops in the cost of solar panels as we've increased the amount of capacity of solar. We've learned how to do it cheaper, and there's lovely feedback loop as we do make more of things, they get cheaper, so we make more of them, and so they get cheaper. And solar has decreased in cost by more than a factor of 100 over the last 3 decades, and is now the lowest source of electricity in a good project. So why it's particularly of interest for Indonesia is Indonesia sits within the Sun Belt. So the Sun Belt is the part of the world that sits between roughly plus 35 degrees and minus 35 degrees latitude, and within this region there are 2 important characteristics. One is that the solar resource is quite consistent. That is that we have very low difference between the different times of year in terms of the amount of illumination. And this contrasts significantly, particularly when you look to places like Europe, where there's quite large variations in the resource between summer and winter, as I'll explain later in the talk. So as well as having a very consistent generation throughout the year, the second advantage is that there are no cold winters. And so the resource is generating energy at much the same times of year as people are interested in having those energies. Whereas if you look particularly to Northern Europe and the Northern US, where there's a need for a significant amount of electricity during winter, solar is not such a great match. Whereas within the Sun Belt, which is where the vast majority of the world lives, 75% of the population of the world lives within this region, we've got this very good match between the solar generation and the demand across the year. So why listen to people from Australia talking about this? So Australia's been leading the world in terms of our deployment of renewables. So in 2018 and 2019, we installed more renewables per capita than anyone else in the world, and in 2020 the Netherlands snuck past us, but we're still sitting in second place. So Australia is rapidly deploying solar and wind in our electricity grid, and so we're doing a lot of the learning that's required to manage systems that are dominated by these variable renewables. And we're installing at rates which are around about this 250 watts per person, 5 to 10 times faster than the world average. So we're installing wind and solar at a very large rate. Importantly, that's all that we're installing. The vast majority of the new energy capacity, electricity capacity that we're installing is through solar and wind, and particularly through solar. This means that our electricity system is rapidly changing. So the graph that you're seeing up at the top right is the last week of electricity generation in the Australian electricity network. So you're seeing brown coal, black coal, orange is gas, blue is hydro, green is wind, and yellow is solar. And if you look carefully at that, there's two colours in that solar. There's a lighter yellow and a darker yellow, and that light yellow is rooftop solar. And so one of the really dramatic things in the Australian context is that a lot of the energy, a lot of the renewable energy is being deployed as solar energy on rooftops in Australia, and that's something which I'll talk to a little bit more as we move through this talk. So if we look over the last few years, Australia's been deploying renewables, roughly changing our electricity mix by about 4 to 5% per year. And so based on projects which are planned and been announced, we're looking at reaching roughly 50% renewables by 2025. So our system is changing very, very rapidly. And we're doing that while maintaining relatively low electricity prices. This change is even more dramatic when you look at one particular region of Australia, and that is the state of South Australia. So the Australian market is made up of 5 individual states, and this is the state which is deploying wind and solar energy faster than any of the other areas. So South Australia has reached the point where there is no longer any coal in the system. They closed their last coal plant in 2017 due to the increased amount of wind and solar that's being deployed within the region. And so in 2021, the total amount of energy generated by wind and solar, there's no hydro in South Australia, was 70% of total generation. And so a lot of the challenges associated with deploying large amounts of wind and solar in a large electricity grid are being taken on by South Australia. What you also might notice within this is there is a very small light blue dot within here, and this is the deployment of a large-scale utility battery within South Australia. So in 2017, what was then the largest battery in the world was deployed around about 100 megawatts with about 1.5 hours of energy storage. And that's playing an important role within South Australia around managing the very short-term variability of solar and wind within South Australia. But the larger scale variations are being managed by imports and exports to the neighbouring states and through the use of gas. But we're varying within that from times where 100% of demand is being met by variable wind and solar through to relatively small fractions at other times. And that's being managed within a grid that is the most reliable in Australia. Over the last 4 years, there has been no load shedding in South Australia, whereas all the other states have had some load shedding due to a failure of a transmission line or a coal plant. Whereas South Australia has operated with 0 blackouts within the state, which is a fairly impressive achievement given the very high fraction of renewables within South Australia. So at the deployment rates which South Australia is seeing, they're likely to achieve 100% of their total demand will be matched by renewable generation in the form of wind and solar. What you'll also see within this, again, looking at this light yellow versus dark yellow, what we're seeing is that at times up to 70% of total demand is being met by rooftop solar deployment. So Australia is a little unusual in that residential customers are installing rooftop solar on their roofs, and that's making a very large contribution to our overall electricity mix. And this deployment is occurring in an environment where market prices are decreasing. So as our renewable fraction has been increasing over the last 4 years, what we've been seeing is a decrease in market prices. That as our market is accepting that we need to change our emissions profile and we need to deploy renewables, we're finding that deployment rate is rapidly increasing, but it's commensurate with increased competition and a decrease in price in the market. So it's possible to both deploy large amounts of solar and to deliver cost reductions in your electricity market, as demonstrated in Australia. So Australia is recognising this rapid change, and we've been doing a lot of work looking at what might 100% renewable electricity look like, or high fractions of renewable electricity. And in particular, now we're looking at as the Australian Energy Market Operator, who is responsible for the day-to-day operation of the market, is now modelling scenarios out to 100% renewable energy in Australia in roughly the 2035 time frame. So we're recognising that these changes are going to be coming rapidly and need to be able to manage a system which is dominated by variable generation. So to stabilise, ideally you want to have a mix of technologies, so it's not going to be just one technology, but it's certainly possible to have systems which are dominated by variable generation and then supported by existing hydro, geothermal, in the case of Indonesia, not in Australia, and biomass. So using those generators to help support the overall system. There's significant benefit by spreading the resources out, so you can imagine that when a cloud mass comes through and the sun might block out a solar plant in one location, by having these resources spread out, you get an averaging benefit by having these resources dispersed across the country, rather than relying entirely on generation within a local system. So having systems connected out across large areas helps to smooth out the local weather effects, and we require, we experience less variability within the overall system. The next thing you want to do is start looking at demand management, and that's particularly looking to shift loads from nighttime through into the day. Traditionally, in the Australian context, we tended to try and shift our energy demand into the nighttime period. And if we look at South Australia, we can actually see this. You can see in the middle of the night there's a little bump within the system, and within our current system, what we have is hot water systems that are turned on at night. So there's this off-peak scenario, and what we're finding is that this is now the wrong time of day within the system. So there's proposals to shift our off-peak time periods into the middle of the day when we have an excess of energy in the system. And we can start to look at various other loads being shifted, shifting refrigeration loads into the middle of the day, and as we start to bring electric vehicles into the system, looking at charging electric vehicles during the day rather than at night, to try and shift the demand to better match the solar profile in particular. But eventually within the system you need to have some storage. Storage is the last thing you want to do if you can avoid it, because storage is fundamentally expensive, and fundamentally it's a loss of energy. That any energy that you store there, ultimately there are losses associated with battery storage or pumped hydro, so you want to avoid it if you can, but ultimately you get to a point where the lowest cost solution is to incorporate some storage. And to be able to shift energy from these periods where we have an excess of energy in the system through to periods where there's a shortage of energy within the system. So in terms of mass storage for the electricity market, we've got two leading technologies, and those are the advanced batteries that I referred to, which are increasingly being deployed around the world within utility grids. That there are now numerous 100 megawatt scale 1 to 4 hour storage systems being deployed around the world. But by far the largest technology in terms of energy storage is pumped hydro. It's more than 97% of the power and more than 99% of the energy storage around the world. And it's also the cheapest source of energy storage. So in terms of supporting the widespread deployment of renewable energies to try and get the weather averaging, then high voltage DC has got a significant role to potentially play within the system. So high voltage DC enables you to move energy very long distances with very low losses. So the largest systems now being developed in China, we can now shift energy 3,000 kilometres at 1.1 million volt DC. Very large powers, we're talking 12 gigawatt scale power, and energy was being lost at only at the scale of 10% losses. And so you can imagine that this really gives you the potential to virtually move energy from one end of Indonesia to the other. And those who are following the renewable energy activities in Australia would recognise that there's a proposal from Suncable in Australia, which is going to deploy solar energy in the north of Australia, so in the Northern Territory, which is south of where the cursor is here, and transferring it via undersea cables all the way to Singapore. And that they see that this project is financially viable to be able to deliver energy all the way from Australia to Singapore. And there are agreements, I understand, between Indonesia and Suncable around the deployment of that cable through Indonesian waters. So the technology is moving along quite dramatically, and the costs, even for underwater cables, are now dropping quite significantly. So in terms of moving on to pumped hydro, which as Ed very kindly pointed out in the previous presentation, is the lowest cost source of energy storage. It's a form of potential energy storage. So when this is the Tumut 3 pumped hydro scheme, which is the largest one that's currently operating within Australia. We have a lower reservoir. When there's an excess of energy in the system, pump water up and store the energy as potential energy in the upper reservoir, and then when there's a shortage of energy in the system, then that energy can be allowed to flow back down the river. So these schemes, if they're on river, like the Tumut 3 system, look a lot like conventional hydroelectricity schemes. And in particular, they often need very large dam walls, and they need to be able to cope with large flooding events. As you can imagine, being on a large river system, when there's a large rainfall within this upper reservoir scheme, you need to be able to manage the flood risk and the flows of water coming down to the river. And a lot of costs associated with these on-river schemes are associated with managing the flood risk, and that 1 in 100 year, 1 in 500 year event where you could imagine that a catastrophic failure due to flooding could lead to a major emergency downstream. So there is another approach that can be taken around pumped hydro, and this is an example of a scheme that has been developed in Italy, which is an off-river pumped hydro. And the aim here is not to build the reservoirs on-river, but to build them off-river. And the advantage here is that you can build then the upper reservoir high up in valleys where there isn't actually a river flowing. So this particular scheme, we're looking at 500 metres height difference between the upper reservoir and the lower reservoir. And the advantage here is that it means that you need much smaller reservoirs to store the same amount of energy. That the higher the height difference is between it, the more energy that you can store. So you can see this scheme here is capable of generating 1 gigawatt of energy for 6 hours between a pair of reservoirs which are only about a square kilometre in area between them, about 500 square metres for each of these reservoirs. So this means much smaller reservoirs, much smaller environmental impact to be able to store significant amounts of energy. And so we've done a significant amount of work to develop an international pumped hydro atlas to ensure that people have a good understanding of what the potential is for pumped hydro around the world. And if you follow the link through, you can then go through to the connection to the national map where all of this data is provided. And at the end of this presentation, I'll zoom into Indonesia and give you a sense that there's a significant amount of potential resource within Indonesia to support the deployment of solar. These sorts of schemes, as I described, are much smaller than other schemes, so there's a very small footprint required per person. We're only talking around about 3 square metres per person to support a system of 100% renewable, so it's not a large amount of area that's required. The mapping that we did excluded all national parks, so all the protected areas that were identified in the world databases are excluded, so there's a vast amount of resource in areas which are not environmentally sensitive. And importantly, the water usage for these schemes is small. The pumped hydro, despite the fact that we're using water as the main storage medium, actually uses vastly amounts less water than coal-fired plants do when we use water for the cooling towers. So the water requirements for these are quite small and are not going to have a large overall impact. So Australia is aggressively pursuing pumped hydro schemes at the moment. So we have a number of existing schemes, but we have a very large scheme being developed at the moment, and that is the Snowy 2.0. This scheme is going to be 2 gigawatts in scale, and it can store 350 gigawatts of energy. So if we think back to the presentation I showed you for a week's electricity generation for South Australia, this scheme could store the entire energy requirements for South Australia for a week. So these are very large scale opportunities, but you can also deploy much smaller scale. So there's a pair of a scheme being developed in North Queensland, which is utilising an old gold mine, and so they're using the pit from the gold mine as the lower reservoir. And this scheme is going to be able to operate at 300 megawatts for 6 hours duration, so store 2 gigawatt hours of energy. So you can have different size schemes depending on where in the electricity network it needs to be positioned and what it's trying to support within the system. We then have another dozen or so schemes which are at various stages of detailed planning and feasibility, as well as numerous battery schemes, but the scale of these schemes tend to be much, much smaller than the scale of the energy storage that can be afforded by pumped hydro. So battery is going to play a really important role in terms of power support within the system, because batteries are very cheap for power. The power electronics are relatively cheap, but the energy storage, the battery cells, are relatively expensive. Pumped hydro is the other way around. The energy generation, the power generation, the turbines, the pumps, the pipes, etc., are relatively expensive, but the energy storage is cheap. So these two technologies are going to play an important role together to balance variable renewables in future electricity grids. So the next stage I want to move through is to try and present the case that the solar resource in Indonesia is much greater than has generally been considered in terms of the work within Indonesia. So this is from your National Energy Plan from 2017. At that stage, the viewed potential resource within Indonesia was considered at 200 gigawatts. My understanding is that the more recent presentation, that number is nudging up towards 400 gigawatts. But I'm going to try and present the case that the potential resource within Indonesia is much greater than that, and I think there's a couple of examples that have come out of your own recent announcements that suggest that this is the case. So the role for solar is important because it is the scale of the potential resource. There is more solar potential within Indonesia than all of the other technologies combined. So it's discussion of marine technology, wind, geothermal, biomass, everything else is relatively insignificant in comparison to solar in terms of the scale of the resource. Importantly, and as I'll come to this again a little bit later within this session, it's a very good quality resource in that it varies very little with different times of year, and this makes it a much more easy resource to incorporate within the system than you might find solar, say, within Europe. Interestingly, it's very good on an average basis, but it's also very good on a continuous basis. So David Silalahi did some work looking at how the variability looked at locally at 1 day, 2 day, 3 day, 4 day, 5 day periods. And once you get to sort of the 2 to 3 day period, the resource was amazingly consistent and much better than I've seen in the work that we've done in other regions around the world. So it means that there's going to be a much lower need for storage over the multiple day, months, weeks type timescales within Indonesia. And the key for storage is really going to be about the day-to-day shifting of energy from the middle of the day into the evening. So there is a lot of options in terms of where the solar can be deployed. So building systems is an important one, given what I mentioned around how rooftop solar is playing a huge role in the Australian context. But we also looked at unused land, so particularly looking at ex-mining areas within Indonesia. We looked at the opportunity to combine with agriculture in Indonesia. The use of floating solar, and particularly looking in the first instance of inland lakes and reservoirs, and there's been some interesting announcements recently in Indonesia around the very low costs that floating solar can deliver, but also to look at the marine opportunity. So rather than looking at using waves as Ed suggested, we're going to look at the areas of Indonesia where there are very low waves, and therefore there's the opportunity to deploy solar floating on your inland seas. And importantly, what's emerging is the cost competitiveness of solar with fossil fuel generation. Indonesia is different to Australia, however, when it comes to the wind resource. So within this is the Global Wind Atlas, which was developed by the World Bank in partnership with some universities in Europe. And what you see there is that what here, redder colours are better. Australia has a very good wind resource. What we find with Indonesia is that the wind resource is relatively low. So there's a few opportunities. You've had some wind deployment in Sulawesi, and that's because that's one of the locations that there is a relatively good resource. And there's some good resource opportunities in some of the high hills through Java. But as a whole, relative to other regions of the world, the wind resource is relatively low. This does contrast, however, with the solar resource. So the solar resource is relatively evenly distributed within Indonesia, and the relatively scale of the resource is very strong. So what we then have been interested in doing is looking at what is the scale of that resource relative to potential electricity demand. So electricity demand within Indonesia at the moment is around about 300 terawatt hours, but we expect that, as we'll discuss later, to increase dramatically moving forward. And if you just do a raw calculation of all of the inland seas, all of the land area for Indonesia, then you're looking at the total resource being some 7,000 times greater than current demand. So a tiny fraction of the land and sea mass of Indonesia needs to be made available to meet all of Indonesia's demand from solar. So despite the fact that solar is a relatively low energy density, there is a vast amount of land and sea resource available within Indonesia to be able to meet current demand. And I'll take you through the case that we also see that opportunity is there within future demand. So at the moment, Indonesia, relative to other regions such as Australia or Singapore, uses a relatively small amount of electricity. So if you look at current demand within Indonesia and then consider the future energy growth, population growth out to 2050, if you were to increase the per capita energy consumption to the equivalent of Singapore, which I think is a reasonable aspiration in terms of where Indonesia sees its economic development heading, then you're looking at roughly a factor of 10 increase in the electricity consumption per person. On top of that, if you then look to electrify all of the other sectors of the economy to eliminate fossil fuels, so look at transport, heating, industrial use of fossil fuels, then roughly you're looking at about a tripling of electricity demand. So what you're looking at there is 27 megawatt hours of electricity per person, which with the future population growth, you're looking at around about 9,000 terawatt hours of electricity consumption to completely decarbonise the entire future energy demands of Indonesia, even in a very highly industrialised future setting equivalent to Singapore. So what you're looking at for that very aspirational use of electricity, if that was entirely deployed by solar, then you're looking at around about needing 2% of total land area, or around about 0.5% of the overall maritime area. And I aim to present the case that I think this is well within the scope for Indonesia. So while Ed talked about waves as a potential resource and marine resource for Indonesia, that is very much focused on this coastline through here. And that's benefiting from the winds that are occurring within the Indian Ocean, producing swells which are coming up onto these coasts. Interestingly though, because you have an equatorial climate, you live in what's referred to on a wind basis as the doldrums. And this is an area with very, very low wind resource. And that means that all of the tropical storms tend to go to the north or to the south of Indonesia, and that the wave events tend to be relatively low within Indonesia. So what we've done is look at data that's come out of the European weather agencies, where they have historic modelling of the world's weather patterns over the last 40 years, and gone through that database to identify when wave heights would be greater than various heights, so greater than 2 metres, greater than 4 metres, and greater than 6 metres within Indonesian waters. And what you find is that a vast amount of Indonesian waters have very low wave heights. And so if you look at maximum wind speeds of 15 metres a second and 2 metre wave heights, there's 130,000 square kilometres of marine area which has these conditions. And these are the sorts of conditions where the opportunity for floating solar offshore could be realised. So if you constrain yourself only to this 2 metre wave height, then there is some 34,000 terawatt hours potential opportunity, which is some 4 times that future optimistic potential future electricity demand for Indonesia. If it's possible to deploy for occasional events, and we're talking once in a 40-year 4 metre wave height, then that then stretches out by another factor of 6, up to almost 200,000 terawatt hours of potential resource. So there is a vast opportunity to use the marine area in Indonesia, not necessarily for direct marine energy, but for floating solar. So where else to put the panels? David Silahari did some detailed GIS analysis of the rooftop opportunity within Indonesia, and what you see there is that there's an opportunity there for 20% of that 900,000 terawatt hours to be deployed directly on rooftops within Indonesia. So there's no need to be putting this on any other land. That 20% of that resource could be made simply by deploying on rooftops within Indonesia. And Australia is showing the scale of that opportunity in terms of that overall resource. That you saw already we're in a situation where at times more than 60% of our electricity demand in South Australia is being met by rooftop systems. Another huge opportunity is agrophotovoltaics. So there's a lot of work being done in Europe, in Korea, and various other regions around the world looking at combining photovoltaics and agriculture. Now it's important to note within these is that there's a lot of crops which this does not suit. So any of the crops which rely on high amounts of sunshine, so things like wheat and rice, any shading that occurs from solar directly leads to a drop in yield from those crops. So if I was to deploy 20% solar over the top of a rice crop, I would expect to see a 20% yield. So this work has excluded any of the wheat opportunities, any of the rice opportunities within Indonesia. But there are a lot of other crops that either are not affected or actually benefit from increased shading associated with agriculture. And so looking at deployment co-located with agriculture, there's an opportunity for 30% to 90% of that future 9,000 terawatt hours to be met from agriculture areas. We've also done detailed analysis of mine areas, so utilising the mining resources within Indonesia. And it's a significant opportunity, but probably less than 10% of overall future demand. And similarly, if you're looking at floating PV within inland reservoirs, so lakes and inland reservoirs within Indonesia, there's probably less than 10% of that future demand could be met by floating PV. But moving to offshore opportunities, so floating solar in the inland seas around Indonesia, we're looking at 4 to 20 times that future demand could be met from solar. And importantly, this is also a low-cost opportunity. So analysis that has been done looking at the costs of electricity in the Indonesia power sector is already seeing that wind and solar are competitive with all of the other technologies within Indonesia. But if we forecast the way that solar continues to be decreasing in cost in future, it's by far the lowest cost opportunity moving forward, with the opportunity probably for a factor of 2 decreases in costs relative to today in future markets. But it would also be fair to say that opportunity is already occurring within Indonesia. So what I was referring to here was this is roughly a 6 cents a kilowatt hour cost what we're already seeing with announcements within Indonesia was that the recent announcements of the floating solar options of prices of around about 3.7 cents per kilowatt hour for floating solar within Indonesia. This has also been recognised within Singapore, so Singapore's had a recent announcement that they're partnering up to develop a 2 gigawatt scale scheme which in reservoirs in northern Indonesia to export that solar power directly into Singapore. So people are already recognising the opportunity for floating solar within Indonesia. Importantly, there's also starting to be deployment of floating solar in marine environments, so that there's plants being deployed off of Singapore in the marine environment, showing that marine opportunity is also there in moving forward. So we've got a vast resource which is also demonstrating that it can deliver low costs. So as I mentioned earlier, Indonesia has the advantage that it's got a very stable insulation with no cold winters, and so we can look to those technologies that I referred to earlier to help balance out the fact that solar is not available 24/7, and it's only generating when the sun is shining during the middle of the day and not at night. But what's important, as I said, to recognise within that is that this is not something that needs to cope with variation between seasons. So I'm in Canberra, we have a relatively good resource. My solar resource during winter is roughly 3/4 of the average resource I get through the year. So we see some seasonal variation where we get better resource during summer than in winter, but it's a modest variation between the two. If we look to Germany, which really kicked off the world's solar PV market development, we see a very, very different story where in winter there is almost negligible amounts of solar relative to the summer resource, and that the winter resource is only about 23% of the average. Whereas if you look in Indonesia, and here's Jakarta for example, we're seeing the resource is very, very consistent through the year. That in the worst months we're still seeing 83% of the average generation. And the other interesting thing with it, if you start to look at what the running 2-day, 3-day average, weekly averages in locations, there's very, very rarely periods where you see extended periods of low generation. That it's not just good variation at a seasonal basis, it's on a day-to-day variation is very low, which means it's very well suited to just needing to have storage to balance the day-to-day variation, rather than the sort of problems with seasonal variation which places like Europe are looking to, where they're really looking to things like hydrogen and seasonal storage to be able to manage both the high demand and the low generation that they see during winter. So coming back to the storage aspect of it, so Indonesia is very well blessed in terms of the potential for pumped hydro. Lots of good high places close to low places. Mountains of the order of hills of the order of 100 to 800 metre height difference are very well suited to pumped hydro deployment. So if you want to follow through to our website, you can follow through to links to this national atlas, where we've modelled pumped hydro opportunities for a range of different sizes. This is particularly looking at 18-hour duration storage for 50 gigawatt hours, so relatively large 3 gigawatt size pumped hydro, but we've modelled from relatively small schemes through to quite large scale schemes. As you zoom onto these, you can start to resolve individual sites. So as we zoom into, in this case, into Java, we can then zoom in further, and you can see the individual reservoirs that are being considered, blue being lower reservoir and light blue being the upper reservoir, with the line showing a nominal tunnel route between these two schemes. If you then go further and zoom into an individual site, you can then click on a site and see the detailed information about these sites. So the class of the scheme, Class A sites are the best, lowest cost sites. They're roughly half the cost of Class E sites that we show in the modelling. We can see the height difference between these, the separation of the reservoirs, and various other characteristics of these individual sites. Importantly, what you see within Atlas is that there's a vast number of sites, and vastly more than are possibly needed to be able to support 100% renewables in Indonesia. And you can see examples here where, if for some reason you find that this particular site doesn't apply for cultural reasons or for societal reasons, there's typically another site close by which is also capable of delivering good economics. So there's lots of flexibility in where these schemes can be deployed. In summary, what I hope you'll be convinced from the discussion that I've had with you here is that Indonesia has an amazing solar resource, and that there's a vast opportunity for solar deployment with Indonesia. And this resource is quite different to the rest of the world because, it's quite different to places like Europe and Northern America, in that you operate within the Sun Belt, where you have this very consistent solar resource and not needs for high energy demand in winter. You have a vast maritime resource. The lack of wind, which might mean you don't have good opportunities in terms of wind farm, is a plus in terms of it means that you have relatively low waves in your marine areas, and so you have a vast opportunity to deploy solar within those. But there's also big opportunities within the rooftop, particularly, and agricultural PV to co-locate solar and PV to be able to better utilise the land availability within Indonesia. There's a vast opportunity for pumped hydro, as we've shown through our mapping resources. And so we're fairly convinced that 90 to 100% solar deployment within Indonesia is something which can be achieved, and is a way for the electricity system to evolve in Indonesia in the future. Thank you very much for your attention.
Thank you very much for that. Yeah, it was an interesting presentation. You were talking about the PV and actually in Indonesia, where the we have huge potential for PV. And yeah, I would like to invite also the attendant. Please, if you want to give a question, just type it in the Q&A, or you can type as well in the chat box. Yeah, Professor Matt will answer it. I've seen as well that David is in the attendant list, and he also wrote something over there in the paper. Yeah.
Yes, I certainly, David is in the audience, and I'd like to acknowledge the really important work he did around mapping this and understanding what the scale of the resource really is in Indonesia.
Yeah. So once again, if you have any question, you can just type in the Q&A or in the chat box. While we're waiting for that, I would like to ask regarding the there's an opportunity actually, there's an opportunity for 100% PV. But then we have problem with that PV is only available during the day, and one of the solutions that we offer is using the one that you are presenting was using pump hydro for that. But have you tried to put the map of the solar potential with the pump hydro potential on top of each other? So, I mean, do we need to have another transmission line in order to balance that out, or they can be in one place, like you have the PV potential, and in the same place you also have the pump hydro potential?
Yeah. So we're undertaking some modelling led by David coming up to look at whether or not there is significant advantage in connecting the different islands in Indonesia. But the comments that I made around just how consistent the resource is, it may well be the case that there's not actually a strong need to interconnect the islands within Indonesia, that the solar resource is so consistent on relatively short timeframes that a modest amount of storage may well be able to manage it in short timeframes. So the preliminary work that David's done there suggests that strong interconnection is not going to be important for the least cost solution within Indonesia, because the solar resource is so consistent across the region. And so as long as it's not all in one spot within an island, then there's enough variation in terms of how the clouds move through and the variability of the generation that you can actually balance it with a modest amount of storage. And basically, roughly speaking, we're finding about a day's storage, 24 hours of storage is what's needed to do shifting from day to night, as well as some degree of storage to manage the variability on a daily basis. So this is quite different to looking at some of the other regions of the world where we've looked at 100% renewable studies, where it's been quite important to have significant hydro storage, conventional hydro, to manage the seasonal storage. So you might use conventional hydro reservoirs to manage the winter peaks or extended periods of wind drought. The solar resource is so consistent that we're not seeing the need for large amounts of other storage within the system.
Okay, yeah. Thank you very much for the answer. We have one question from Pak Eko Prasetyo from the DGB. Yeah, it's still in correlation with that. I mean, how is it in Australia? How is it in Australia when you start having, like right now, you like 70% of the in southern Australia, the demand was fulfilled by green energy, right? How is it? Do you build a new transmission system or distribution to support all of those, or what? Because what Pak said, in the middle part of Australia is the best of a lot of solar potential over there. So in terms of price of EV, then yeah, it is low cost. But then if you need to build up a new transmission system, I guess you also mentioned DC and cable, like something like that. So in terms of the whole cost, it might be expensive, or it might be not competitive anymore compared to the other. How is it in Australia?
So there's a series of stages that occur through the transition. So if we look at the Australian market as a whole, we're still quite early. It's 20-25% variable wind and solar within that energy mix. So that almost looks a bit like variable demand. So you can kind of imagine that that's just decreasing the residual demand. And so the existing system can manage the flexibility within the system. So coal plants are starting to have to ramp down during the middle of the day. Gas plants are operating less often. And so what we're seeing there is mostly we're managing within the flexibility of the system. So what's starting to emerge now is so a lot of the wind and solar were built in locations within the existing transmission grid, and there wasn't really a need to build additional transmission to support that. So the next stage is transmission build is starting to become more important. So South Australia is about to build a significant connection into New South Wales to enable more wind and solar deployment within South Australia, and then they can share that energy with more of the state, other regions. And so transmission can sort of average out the fact that there might be a bit more wind in South Australia at the moment, and a bit less wind in New South Wales, and shift energy around that way. So transmission sort of becomes important in that next stage of the transition, and that's what we're seeing in Australia. There's a lot of planning around what is referred to as renewable energy zones, that we plan to build a transmission to areas which have a strong, in Australia's case, wind and solar resource, and be able to manage it that way. Because Indonesia is going to be dominated probably by solar and then supported by storage, it's probably going to emerge quite differently. And what I see is more likely to emerge there is trying to build the pumped hydro and the solar relatively closely together. So most of your power is being moved over short distances, and then the pumped hydro is averaging out that variability through the day, so moving that energy to where the load centres are. So I would expect that there's an opportunity within Indonesia, with good planning and thinking, that there'll be much less need for transmission build than there is, because the solar resource is much more ubiquitous, and you can also see that the pumped hydro resource is quite widespread out, that there's lots of areas. It's not like in Australia where we're trying to hunt out the best locations for wind. Solar varies very little from whether you're 100 kilometres down the road or 10 kilometres down the road or 1,000 kilometres down the road. It all much looks the same. So it will probably evolve a little bit differently. Where will be interesting is more, I think, around the distribution system, so what's going to happen within the cities and what the scale of the opportunity is for residential and commercial batteries to manage much of the local that local rooftop solar deployment without having to need for significant upgrades in the distribution system to have power pushing out of the system during the middle of the day.
One last question from Mr. Iswan from Jalan Jepang. You mentioned that in 2017 there was the new largest battery at 100 megawatt in capacity in Australia. So when we are talking about the batteries and the pump hydro as a product, how does that compare to the other? I mean, what kind of advanced battery is it better to use the battery as compared to pump hydro, or do you have comparison to that?
Yeah. So the Hornsdale Power Reserve, or the Tesla Big Battery in South Australia, was the first that was deployed in Australia. It was about 100 megawatts, 137 megawatt hours at the time, but it's been increased in size since. We're now seeing that there's about 10 scale of that sort of scale, around the 100 megawatt scale, being deployed with those typically 1 to 2 hours of energy storage duration. Those are largely being deployed for ancillary services, so managing the variability of the power system, so ensuring that the frequency is well maintained by chasing the little variabilities in power that comes as demand and supply varies in the system. So a lot of those schemes are going in where existing coal power plants are either retiring or have retired. So there's already good strong transmission and they're in a good strong part of the network to be able to provide support for the overall system. So that's that next stage of the transition for us is managing the frequency type aspects with these lithium-ion battery systems. And then pumped hydro starts to become more important as we start to move from that 50 to 75% part of the network, where it moves from power fluctuations being important to managing energy variations within the system, to being able to shift the energy in time within the system. So at the moment, batteries are largely lithium-ion systems with inverter-based control, and they're increasingly being deployed within the system. And within South Australia, the Hornsdale Power Reserve is now being used to provide virtual inertia within the system, that it is aiming to respond to frequency variations on the millisecond scale to inject and extract power from the system, just like a big spinning mass would if the frequency varies. So they're quite powerful in terms of their control ability to be able to support the stability of the system. And as I described, South Australia has not had any power shedding in the last 4 years. It's been quite impressive.
Yeah, despite that we have a lot of renewable energy with the radiation.
Yeah.
Okay. Thank you very much, Professor Matt. This is a really nice, really interesting topic, and for sure we want to have more time, but unfortunately we cannot do that. We still have another presenter right now, or another invited speaker, that will present after you. So also I would like to say thank you very much, Professor Mat, for your coming, and also David, David Silalahi, also supporting Professor Mat and of Andrew Blackler from Australian National University. So thank you very much, and we will move to the third speaker. I would like to invite Professor Joseph from Auburn University. Are you here with us, Professor Joseph?
Yes.
Yeah. So as a recap, we have been discussing regarding the potential of wave energy in Indonesia. So we start from the ocean and then we go to the sky, which Professor Mat said that 100%. Indonesia has a large potential of EV, so we can have like 100% power comes from EV or solar. So the next point will be delivered by Professor Joseph, and we would like to see how we can build a system, right? Because what we are talking about is the transmission system and stuff like that. It's a huge interconnection. Now, how about if we try to make a small system, microgrid? So yes, are you ready with your presentation, Professor Joseph?
Yeah, definitively. Yeah.
Yeah. So while you are preparing for your presentation, I can read some CV of yours. So Professor Joseph is the professor at Energy Technology in Aalborg University, Denmark, starting from 2011. So he received his PhD from Barcelona Tech in Barcelona, in UBC Barcelona in 2003. And the newest one, he received the IEEE Bimal Bose Award for Industrial Electronic Application in Energy System for pioneering contribution to renewable energy-based microgrid. So, and it was received in 2021. So he just got it. So, without further ado, I would like to give the floor to Professor Joseph. So, time is yours, Professor Joseph.
Yeah, thank you very much, Rory, for the presentation. Well, what I want to introduce here is, as you mentioned, the concept of microgrids. And I will go through some of the roadmaps that we have been crossing in the last years in the Center of Research of Microgrids. This is the AAU Energy in Aalborg University. And then you can find more, let's say, information in our website, crom.it.edu.k, and here we have also the email address. I want to start with the forewords of this man, John Kabat-Zinn, which is very famous for in the mindfulness area, which he said, the little things, the little moments, they are little. And I think it happened kind of the same with energy systems. And when we start with the microgrid concept, it's something that some people and organizations struggle to have definitions, but it's very hard to have it because of there is no limits about power and energy when you scale up this concept. So this kind of concept is more, let's say, a philosophy of trying to generate, store, and consume near each other and in a sustainable way, and has been expanded to many other areas like water, what is called also micronets, and food. So these are some of the members of our center. We are around 50 people working in the microgrid area, and what I'm going to present here is part of their work. So this is for acknowledgement. And of course, another important thing is our laboratory setups, in which we deploy microgrid facilities. You can see here some of the view of the laboratories, in which each of these cabinets demonstrate a microgrid. We have also these distribution systems and also
grid simulators. And normally what we do is going from MATLAB simulating codes or simulation codes to deploy fast prototyping by using hardware in-loop systems, but also integrating real smart meters like we can see here. So we basically use all real electric equipment, and what is generation, consumption, and storage, it's let's say virtual. No? That's another thing. It's like we can deploy a number of microgrid systems in a single point of connection, what is called multi-microgrid systems, but also multiple connections. So we have a geographical distance between them, what is also called the virtual power plants. And we have also a demonstration house here in Auburn University. And these are some pictures because maybe, for instance, Ronnie was one of our PhD students and then research assistants here some years back. And here you can see also some of the projects we are developing, for instance, with the company Zonen, to develop the next generation of battery systems that will be implemented in our houses. So also talking about batteries, as we heard in the last presentation, is something very important, but also going to residential. And which are our research frameworks in our center are microgrid clusters, digitalization, digital twins, and IoT, maritime microgrids. We heard also in the last presentation about what happened with the maritime energy systems. So here we focus more on ships, ports, electrification, and also offshore wind. And then I will talk a little bit on electrification also out in space. Nanosatellites, lunar bases, and also closed ecosystems. So first of all, I want to talk about artificial intelligence. Many people is talking right now on integrating more and more artificial intelligence, but I'm not sure if sometimes when we integrate this kind of technologies, we really know how our brain works, because we know today that we have in our central nervous system, which is basically the mind or brain, we have around 80,000 million neurons. However, recent discoveries has been shown that in the heart we have around 40,000 neurons, and in all the digestive system we have around 500 million neurons. So it's really like a distributed system. It's not something that is centralized anymore, and this is something that we have been tested. We now know also that we use 100% of the brain, because in the past some people said, well, maybe we are using 5% or 10% of the brain, so relax about this because we are using 100%. However, simultaneously we only can use 4% of our brain, and around 2% of the brain, which is about 4 watts. Yeah, so you can imagine that we have a lamp of around 4 watts in our brain, and this is due to the glucose and oxygen limitation. However, we normally use similar neural network paths, and that's why sometimes it's difficult to change when we want to change. Yeah. So I think it's also interesting to see how this brain has been going through an evolution from the reptilian brain, which have 500 million years, and then the limbic brain, and finally neocortex. Reptilian brain is more action-reaction brain, looking for opportunities, while the limbic brain has been developed for the mammals. So basically, if you think about your dog, if you have a dog, it's able to have emotional and feelings, which is something that reptilians don't have. And then at the very end, only 100,000 years, we have this part, the neocortex, which is connected to the rational thinking brain, and especially the frontal part, it's the one that we have, the human beings, that allow us to go into the future and and come back to the present moment and take decisions. So decision making is very important here. However, our brain, and this is because of these 200 million years, are very, very important. Sometimes emotions comes with decisions, and then the rational part is the justification. And also that's something very important. Another exciting findings here are, for instance, this is coming from the Hermann Institute in Germany. It's that the heart also is generating hormones like oxytocin, which is the one who gives you love, trust, and fidelity. So it's not just a pumping blood organ, but it's something else, our heart. And also in the same institute, they make measurements showing that there is more communication going from the heart to the brain than from the brain to the heart. And that's also something pretty amazing. If you look at our brain, we have normally the thalamus, which is the part which synchronizes the cortical activity. And then we have the amygdala, which is the one who has the emotional memory. This amygdala sometimes is also activated when we have, for instance, bad mood. Well, anyway, if you have questions, I can answer at the very end about this. But here you can see what happens when we are in incoherence between what is the heart and the brain waves. When we enter incoherence, you can see that this facilitates the brain function. You can see here that our heart rate, some people think that is something that has to be something constant with a number, and it's not true. What you need in your body to be constant is the blood pressure, and you make it constant by changing the heart rate. And this heart rate, you have many ways of change. For instance, when you are in incoherence between the heart and the brain, you come with frustration, anxiety, worry, irritation, some of these feelings. You can see a lot of harmonics here and not non-periodic waveforms. However, when you feel positive emotions like appreciation, love, courage, that by the way, when we feel this, we have seen that the neurons in the heart are activated. So now you understand a lot of things that we say sometimes. We say something from the heart and etc. You can see that we almost have a pure sinusoidal waveform from the heart rate. So really we can see those kind of emotions from these heart rate waveforms, and then we can see also this coherence between the heart and the brain. In terms of magnetic field, also we know that the magnetic field of our heart is 5,000 bigger than the brain, and it can be measured up to 2 or 3 meters, probably more. And this allows us also to synchronize, for instance, hearts. And a lot of experience has been done also between, for instance, people that has autism together with their pets or horses, etc. So that's really exciting. And you can see also similar things also on ongoing how we are developing control. I will explain you a little bit about this. Here you can see a typical microgrid system in which we have renewables, for instance, in which they inject all the power that they can and then connect it to a battery system. However, to cope with, let's say, this kind of small system, when the state of charge of our batteries go higher and higher, frequency is changing, so increases a little bit, and then our, for instance, voltage generation, what they will do is to detect that the frequency is increasing, and then automatically they will decrease the power. This way, the microgrid is not able to balance internally the energy, but they will be also compatible with the grid, so that when we have in the grid a lot of synchronous generators, you know that when the frequency is going up, it's because we have more generation than consumption, and then renewables can react to that. I think that this is amazing, and this concept also has been turned out to also be implementing what we call also grid forming inverters or virtual synchronizers, in which we try that our power electronics converters try to behave like a synchronizer to be also compatible with the grid. This is something we can do traditionally, for instance, with wind, because we have some inertia or mechanical storage. But when it comes to solar, additional energy storage systems has to be deployed, and this is something very important. I want to show you also how inertia helps also the synchronization. This is just one experiment in which you have a number of metronomes, and if we want them to be connected to the same system, this is in a platform, you can see that even though we can start connecting them out of phase, they are finally synchronized because this platform acts like the power grid. It's a floating platform that we just change. And then we have these mass balls, which they act like the inertia. So when we connect them, what we are using is the power grid as frequency as a communication link, and this is called also side communication, right? If we go a little bit later in time, you will see that all of them are well synchronized. And this is exactly what happened with our power system. When we go to microgrids, we try to do the same by implementing those kind of virtual inertias. And we have also a 3-level control system, very similar as when we have big power systems, in which you can imagine that they create something very similar as in our brain. We have the primary control, which tries to share active and reactive power. So it's a very reactive control, saying that just look at how active and reactive changes, we will adjust frequency and voltage. So it's kind of very similar as our reptilian brain, right? Very reactive. And then we have the secondary control, which adjusts frequency and also voltage, because as a difference of the big power systems, we have a lot of link between the voltage amplitude and the active power, because we have a lot of resistive lines, which is kind of different as the transmission line, which is more inductive. It could be seen also this part as our limbic brain. And then we have our tertiary control, which is basically energy management systems, those that are able to go into the future, come back to the present moment, and take decisions as we have in our neocortex. So I think that this is very exciting, because this gives new insights into implementing artificial intelligence more connected to what has been known in, let's say, by the nature. Now, not only we have a lot of interest when we go to, let's say, inland microgrid systems, but also we can see that the ships are becoming a microgrid, having their own generation, consumption with the thrusters and propellers, and storage with more batteries inside. So this is one of the first electric ships. It's a cruise ship, the Queen Elizabeth II. Still we have diesel generators, but this makes electricity more flexible, let's say, so consumption reduced drastically. And here the problem was that it was just a single, it was a single wire bus, so just with some short circuit or whatever the fault we have here, the whole system went down. And that's why in major part of the ships we can see today that we have separated 2 buses and also you can see a number of generators here, transformers, and the propeller part, which is a lot of them based on thyristors due to reliability. And of course, batteries and fuel cells are becoming more and more trending. Also, multiple microgrid systems are important here, connected also with this standard from 2015, in which we divide the electric system of the ship on a number of microgrids, so that if we have a failure in one of these microgrids, we could isolate the fault and still the system will survive. Another trend is to have AC/DC hybrid microgrids inside our ships, and this is because, for instance, when we want to integrate diesel generators, you are going more to AC, but probably if you want to integrate battery system, you go more to DC. So finally, you need kind of a hybridization inside the ship, and also sometimes you will need the port connection, so that you could inject power from the port to recharge your battery systems. I will show you some nice examples about that. And this is just to show that we can go not only on AC, but also moving to DC is really a trend inside the ship. So having a DC system or DC ring inside the ship, you can see right now a lot of these ships moving into that direction. So from the old-fashioned AC ships, let's say, in which they had an AC main switchboard with all the connections to the generators and going back to the propeller system. Right now, what we can see is some companies, like for instance Siemens, they propose to have one cabinet or two cabinets with all the power converters inside, moving to DC, pure DC systems, and from generators, AC to DC, and then from DC to AC to the main propellers. Yeah, this is just one picture of these kind of, let's say, racks, embedding all these power electronic systems inside. But then ABB came with another concept, which is integrating those converters as closer as possible with the propellers. So those motors have embedded also the power converters, and this means that you can reduce losses, but here you have to increase a lot of the voltages. Which are the voltages we are talking now are probably 3.3 kilovolt or 6 kilovolt, which really is a problem, especially for the circuit breakers. So here you can see the concept. If those circuit breakers has to move to medium voltage, then it can be really a problem to get devices that are already tested in the field, for instance, for more than 20 years. Especially in marine industries, is very important. Then the move from AC to DC, it's also very, very important here, because our synchro generators, they operate in only one, let's say, optimum operation mode when we have a fixed frequency operation. If we move to DC, we can select the best operation mode for our synchro generators, independent from the frequency that we want to achieve. And this really makes the difference, and you can see a lot of studies also from Singapore and many other countries that they are really moving to this direction. On the other side of the coin, what we can see is that some people are starting to propose that instead of moving to DC, we could have variable frequency. So we could accommodate the frequency of our, let's say, main bus to the diesel generators. And this is something exciting, because you can see large cruise vessels of more than 20 megawatts having more than 6% of increase of annual fuel savings. And this is something really very interesting. And moving also to electric, when you, for instance, break your shaft generators, so you just slow down your ship, then you can have also regeneration modes. So you could make your generator to act as, your motor act as a generator, and use the electricity back to your power system, and even put in some energy storage if it's necessary. You can see some vessels like the platform super vessels. They are today, for instance, assessing or supporting offshore wind platforms. And it's very important that also we make those vessels more and more clean. So those are also moving, some of them to DC. And you can see also a number of ferries. This is a past project that we did with Taiwan, in which we electrify a ferry with 4,500 passengers per day. And what we did with this ferry is to remove all the old-fashioned motors and to put power electronics inside. You can see here a couple of diesel generators with the connection to the grid, and then AC to DC converters to create a DC microgrid connected to a battery system. This was around 100 kilowatt hour battery system, and then the propellers. So this was really an exciting thing because we placed all those battery systems and we really cleaned the area. So this is something ongoing in many areas of this world. But also it's very important not only to make our ships greener, but also our ports, because some of the ships that arrive in the port, for instance, with a lot of fish, they need electricity, and for the freezers, for instance, and the first thing that they do is to start these generators, and then they pollute the area. So right now what we have is a lot of these ports having the possibility of connecting the ship to the shore by means of a connection. This means that we need to rethink the electricity infrastructure inside the port. So we need to increase energy and power connections in the ports. And this is something that also we could do with renewables, and we are doing these kind of things here with wind turbines, but it could be done in many other ways. The connection from the shore to the ship, it can be done by having a charger in the part of the port. So this means that we will have a rectifier that will be connected to a DC bus, and the other is to have inside the ship. So it happened a little bit like it's happening right now with electric vehicles. You have a small charger inside the car, but also you can go to a fast charging station, and you can get from the charger directly on DC to your car. Yeah, with, for instance, a charger. Indeed, some of these systems, especially for ferries, they work with standards like electric vehicles, like the charging one. And this means that depending on which is the ship that are arriving to our port, some of them come with 50 Hz, some of them come with 60 Hz, depending on the country. So we need a power converter to adjust the frequency here. And this means that more opportunities to have DC distribution systems are here. Another important issue is that those converters that are placed in the port should be the ones to be synchronized with the ship. Otherwise, according to some experiences in Poland, we could have huge inrush spikes due to the inertia of the generators in the ship. So this means that we need still to do more things on the electric side of the ports. Still in the ports, you can see how port cranes is another issue related to pollution, because still we have a lot of diesel-based port cranes. And we need to electrify this. And you see, if we electrify these kind of systems, when we lift up containers, of course, we need to inject power or energy, but when we are lifting down the container, then your motor can act as a generator. So instead of just burning the power in dummy resistors like today, we could reduce this electricity inside the port, or store, for instance, in flywheels, as we did in another project, or inside the same power system to reuse. This gives us, depending on the studies, around 40 to 50% of energy recovery, and this is a lot. And at the same time, we can lower down the power consumption of the peak. I'm talking about power peak of consumption of the port. So there's a lot of things to do in the ports. And then when we think about ports, electric ships, and so on, then we think also about the electrification of the sea, let's say, with offshore wind farms. Yeah. And as I come from Denmark, this is the first picture. It was an illustration of an offshore wind farm in 1977. At that time, it didn't exist any offshore wind farm, but someone already envisioned that. So always, as you know, first comes the vision of the dreams, and then it comes the reality. And this is the first offshore wind farm, almost 15 years after, in 1991. The first offshore wind farm in the world, it was placed in Denmark. Today it looks very small probably, but I will say that also small is beautiful, right? And today we can see how these wind turbines has been increased from those old-fashioned ones that was just half a megawatt till more than 10 megawatts that we have today for offshore available. However, still renewables are being always looked and sometimes giving people a lot of things to talk. For instance, it was in August of 2019, 2 years ago, that it was in UK it was a blackout. And what happened here, it was a combined cycle, a power plant of 700 megawatt was disconnected from the power grid, it was shut down, and then the frequency started to go down in the system, and then we had in the Hornsea an offshore wind farm. When they detect this frequency so low, they just disconnect, and finally it was a blackout, only for 15 minutes, but enough to hang up all the computer system from the subways, and it was a huge collapse during the whole day about that. And then people start arguing against renewables, and I will say, if we could have renewables but with capacity of grid forming capacities, then those kind of things will not happen, because we will be always supporting and creating the grid. So it's not about renewables, it's more about how we use renewables. So that's why also we have one project which is called Wind Flag, in which we are integrating wind farms with the possibility of working as a microgrid. So supporting, let's say, creating a grid, and more than supporting frequency and voltage, they are participating in voltage and frequency of the grid. So they are able to also operate in island, and they are able to also operate with very weak grid conditions. That's something that is happening right now. So a lot of people are talking about this transition in renewables from grid following to grid forming. And I will say that this is something very important. But now, when it comes to this point, people ask about, should we have additional energy storage systems in our wind farms or solar farms? Or who's going to pay for the power that is not going to be generated because we are having a voltage source that not always will provide all the available power, for instance, from the wind or the solar that we have there. That's why still it's under discussion in a lot of countries and companies. But you can see also that in wind farms, we have also still hierarchical controls implemented, and a lot of them also still inspired on how microgrids work. Today we have also proposals like having, when we have multiple wind power plants, to have a centralized controller, but right now we can see that there is a trend to have a more decentralized and probably a hybridization of those, having controllers distributed, but also one of them, for instance, it could be the centralized control that is connected to our TSO. Now to finalize, I want to talk about space microgrids. So we finish with the Earth and we start with the space. And there's a number of small satellites around the world. And here, this is the work that we have been done with Home Space, which is another company placed also in Aalborg, in Denmark. And you can imagine that nanosats have needs for solar power, and then they convert this to DC, and then we have battery systems inside. So it's like a small DC microgrid system with a number of payloads also that are changing all the time, so very dynamic system. Here is the spectra that we have in terrestrial applications, and you have a lot of changes here due to the atmosphere and limited energy. However, when we go out in space, still we have around 50% of energy more that we could use, and almost let's say a very smooth spectra that we could use. So we have a lot of solar energy available there out in space to this air mass zero. That's why more complex solar cells has been developed recently, so that you can imagine that triple junction and also four junction solar cells are coming, in which all of this different is like a multi-layer system. So each of these junctions is optimized for certain range of frequency. So you can imagine that if I have 3 junction system, each of these layer is optimized for certain range. So when we add all these ranges together, we have a very high efficient solar cell. We talk right now about more than 30% efficient solar cells for space applications, which is really amazing. And then we need independent converters to obtain the MPPT of each of these solar panels that we have in each of the face of the satellite, let's say. And then we have battery packs. And then we have here unregulated loads, and some of them needs for regulation. Right now, we are also studying the impact of solar storms and cosmic radiation of our solar panels, especially electrons and protons. According to our studies, also electrons are impacting the solar panels, and we have been work on the degradation models that, if you're interested, we can share with you. Some of them are public now. And then the other important thing is, like, if we have a microprocessor or microcontroller here, due to solar storms, protons are impacting over the microprocessor, and then all our CMOS digital system will affect by what is called also latch up phenomena, which means that our CMOS will be latched to always one logic. So this means that our microprocessor can be hung up, and this means that our controllers in the space are basically using analog electronics for the control system, which is something very particular, because we thought that analog electronics were not there anymore and now are coming back for make this kind of control. You can see here how it's the trend, increasing the efficiency of these solar cells. Some of them are triple junction, some of them you can see here, last generation, 4 junctions, and here is the efficiency, more than 30%, moving to 33% of efficiency. And here you can see some of the, let's say, microgrids for nanosatellites, in which we have been also collaborating with Space. Those are lithium-ion batteries, very similar as the ones that we have in electric vehicles. And another thing you have to hear very carefully, it's like if you have a geostationary satellite, you will have one eclipse every day. Every day you have an eclipse between the satellite and the sun, you have the Earth. So that means that you have some period in which you have maximum generation. You have to store part of this energy inside the battery system, but then you will have a long eclipse in which your batteries have support for the payloads. And this is a huge impact over the battery systems, in which temperatures are changing drastically, and you have to totally charge and discharge those batteries. You can see also examples, exciting examples, for instance, in the International Space Station, in which you have around 33,000 solar cells producing 240 kilowatts. Batteries has been replaced by lithium-ion batteries recently. So all the old-fashioned technologies are removed. Right now it's like an electric vehicle. And it was in the past made by AC distribution systems. They rewire everything, and right now it's a DC microgrid system. Due to efficiency, due to avoiding reactive powers and many other problems. So it has been just, you can see there are like the primary power system in which we have generation and storage, and then the secondary power system in which we have a number of unidirectional converters interfacing 133 to 177 volt till 123 to 126 volt to a number of loads, which if you imagine that you have electronics, computers, etc., major part of them are working on this. So it's really a perfect match. And now I'm going to present part of our last work, which is to develop microgrids for lunar base. You know that there's a number of projects right now for going to the moon, and that's why it's very important to deploy their energy systems. And you can see here the way that we install solar panels. This is a crater. Right now there's a number of craters that are under discussion, and you need really very high towers. Yeah, we are talking about hundreds of meters to put in the crowns of those rings of the craters and to extract the power that will be used inside. Yeah, you can see here the number of craters. This is the near side of the moon, and this is the far side. There are basically two craters that we are studying. One is the Peary crater, and the other is the Shackleton crater, which is in the south. And here you can see the Shackleton crater. This crater has been studied for NASA of around 15 years. But right now also it looks like Peary crater in the north pole is also very attractive. You can see in red points, you can see the highly illuminated areas in which those PV panels may be placed. And the other exciting thing is that not only we are envisioned to deploy energy storage systems like batteries, lithium-ion batteries, but also to include regenerative fuel cells, which is something very important. So you could have electrolyzers, and you can go for that. Still, some people are proposing nuclear, and I think it's a big mistake to repeat things that we know after Fukushima and many other problems, to repeat that. But I can tell you that it's in the agenda of some companies. The proposal here is to have in the Shackleton crater a number of microgrid systems with photovoltaics, of course, and battery for the lunar habitats, in which there is also a ramping project for that, to have more people there. And then we will have laboratories and charging stations for rovers and electric vehicles. So everything is going to be electric, and this is amazing. There is no oxygen that will lead us to use burning materials, so that's very good. And we will have also in situ resources that we will have to exploit. So this means that a lot of goods are going to be manufactured directly in the moon. So we will not have a total dependence with the Earth. So a lot of resources will be developed there. And then we will have communication systems between all of these different microgrids and of course with the Earth. But we cannot depend on the communication with the Earth because it takes around 15 minutes to have communication back and forward. So we are going to deploy also in the moon a number of satellites. And this is something amazing because this means that those multi-zone microgrids, we envision that they will be interconnected as a multi-microgrid system. Because out in space, we cannot accept a single point failure system. So that's really the most resilient one. And of course, hierarchical control architectures, like I was showing before, has been proposed for that, like having electric components on loads. And in this first level, we will have reactive controllers. Yeah. Now you can think also about the reptilian brain if you want. And then subsystem controllers. And finally, the mission managers. Yeah, more like the neocortex thing here implemented in the one. So we are going to need this kind of hierarchical control. And finally, I want to show you very fast because I think I'm funny.
Yes, exactly.
One of our projects together with the European Space Agency, in which we expand the hierarchical control of microgrids to closed ecosystem. What is the closed ecosystem? Well, if we go out in space, we'll have to generate our own ecosystem. So this means that our crew members will have some waste, and we can reduce especially urine, which have a lot of ammonium, to develop nitrates that then will have microalgae and higher plants to provide for food, remove CO2, and provide water and oxygen. We have been done some tests together with the Autonomous University in Barcelona, in which we have a number of compartments, the nitrification compartment, the photobioreactor, the higher plants, and our crew members right now, they are rats. And what we have done to control this system is to make a parallelism between closed ecosystem and microgrids. So we have here, when we see the photosynthesis, it can be seen as photovoltaics. When we have oxygen storage, it's very similar as when we have energy storage systems. And here, in a closed ecosystem, we have microbial fuel cells, which has a very similar behavior as a hydrogen fuel cell. So as a result, we have been implemented also a hierarchical control, very similar as the ones implemented in microgrids, and very similar if you think about our brain structure. So the primary control, instead of power sharing, it's working with mass flow regulation. Secondary control is making corrective actions, prescriptions, and flow dispatching. And the tertiary control, the same as we have as energy management system for microgrids, here it's trying to find the operation, the more optimum operation points for the entire closed ecosystem. And the results are amazing because you can see that the oxygen generation by using light, it's very, let's say, it's a response, very, very similar as we have with photovoltaic systems. And the oxygen tank levels that we fixed, they work very similar as the state of charge of batteries. Here the difference is like we use hundreds of state variables, and they are highly nonlinear and a lot of coupling between them. But I will say that the results are really nice. You can find this, we published this early in an Industrial Electronics magazine. Well, I want to finalize this presentation with a statement from Albert Einstein. He said, we cannot solve our problems with the same level of thinking that we create them. Thank you very much.
Great. Thank you very much, Professor Lester. Yes, it was an interesting presentation. So you bring us up high to the moon.
Yes.
Unfortunately, we need to go back to the Earth right now. So yeah, we have a lot of questions, and thank you very much for your presentation and explanation regarding the microgrid. Not only in one particular area, but you mentioned, well, I mean, from the figure in here, it goes to the satellite as well. And we would like to put it in a context in Indonesia, because we have islands in Indonesia. And yeah, we have one question from Pak Rusnanto about the microgrid. It might be suitable to have microgrid for electrifying a remote area like islands in Indonesia. And because there are scattered area, and those centers are scattered not only in one place, so it might be microgrid on that. But the question is that Pak Lesnanto has is how about the size of it? I mean, which one that is suitable for that? Like, is it in the low voltage?
Yeah. That's a very good question. We are right now developing a project together with Indonesia, in which we are working on different possibilities of microgrids. We are looking into Medan Island, which have some collaboration with Denmark and some other parts of Indonesia. But basically here what we propose is three different architectures. One is microgrids relatively small in the level of kilowatts, in which can be placed in a container. So when there's an emergency in which you have floods, you have, for instance, volcanoes, you have earthquakes, whatever, maybe the area is without electricity and water is also cut. So we arrive with this container in the truck and we restore electricity and we are able also to produce clean water. This is in the level of kilowatt, let's say. Then when we want to move forward, we have islanded microgrids, which fit a lot with many places in which you need electrification in some of your islands. And this is moving to the level of up to 1 megawatt, let's say. So hundreds of kilowatts, only 1 megawatt. And then the next level that we propose is to have microgrid clusters. So this means that in one area you could have a number of microgrids interconnected between them, and finally those, they could create the grid and they could be also connected to the main grid. So this is what we are right now looking with Indonesia, and of course we are open to collaborate with people here, because we really believe that there's a number of solutions that will match Indonesia. So I think that those three possibilities could be very suitable.
Thank you very much. And as this presentation, like Professor Matt discussed, and I guess in your presentation also discussed regarding the storage, would that be suitable for using storage in an island, or is it must to have that one, or it can be an optional for that? Or I mean, in some application like the satellite, you must have it. Right? When you presented the condition during the eclipse, right? So that is must. But how about in island, like in Indonesia?
Yeah, correct. Yeah, there is indeed a study, and I want to come back to Medan Island and Lombok. I think it's Lombok.
Lombok.
Lombok. Yes. Recently, there is a study a couple of years ago made by Danish authorities and Indonesian authorities, and they show that there's some big diesel generator plant, and we want to substitute this big diesel generator plant by photovoltaic system. Of course, if you want to balance the grid, you will need energy storage, and there is the study of how much energy storage you need to balance the grid in that situation, so that you can remove the diesel generator, but still you can maintain the frequency, and that's why energy storage systems are so important for these applications.
Okay, good. Thank you very much for that, and thank you, Pak Lesnanto, for your question. So we would like to invite another audience for questions. So if you have questions, you can type in the Q&A, or you can type in the chat as well. So we have a question from Mr. Eko Prasetyo from TGB. This is regarding if we have a fallback condition, like for example in the California, if I'm mistaken, that the grid, the transmission grid, fail, and the microgrid become a backup for that. Like you have a one single big transmission grid, and then whenever there's a failure for that, then you can have a separate islanded system. So it becomes like a backup for microgrid, become a backup for the main grid.
Yeah.
Yes, sir.
Yeah, that's a very good question because traditionally some people look at microgrids like having, for instance, photovoltaic systems directly connected to the grid, and they are working like grid feeding. So this means that always they need the big power grid to support voltage and frequency. When we talk about microgrids, they are also participating on this voltage and frequency. So this means that when you disconnect the microgrid from the conventional grid, still you have voltage and frequency stability because they are working as grid forming converters. So finally the answer is yes, we can do that by using equipment that can work as a grid forming, and there is already equipment existing in the market that they can work like that. Maybe you go back 20 years ago, it was a lack of equipment for that, but right now we have plenty of this. So the microgrid will work as a backup for the main grid, because right now we are able to swap between grid connection mode and islanded mode in a very, let's say, seamless fashion. So that's something that today microgrids can do. And then when the grid or the main grid is coming back again, you can resynchronize your system and reconnect them to be connected to the grid. So I will say that this is right now a reality, and this is something that is very good, I think, especially in the case of Indonesia, in which a number of blackouts can occur along the year.
Yes. Good. Thank you very much. I think we don't have so much time for this question and answer. So I would like to appreciate Professor Joseph for coming and for having the presentation from him. So this is the end for the invited speakers. Thank you again, Professor Joseph. Thank you for your time. And of course, we would like to have the, if there is a question from the audience, we will send it to you, and then we will email to you, and then we will receive the email, and we will spread out the question and the answer to the audience. So it is quite interesting from the three presenters, the invited speakers. The first one from Professor Edward Mulyani, the US. He spoke about the potential having the wave energy, ocean renewable power generation. And then we have the second invited speaker was Professor Matt from Australian National University in Australia. He spoke about the potential of having 100% EV in Indonesia. And the last one, Professor Joseph brought us to the moon. Microgrid is everywhere. Microgrid is everywhere, and there are a lot of emerging technologies in using microgrid. In Indonesia case, it is actually there is a project that will be or currently being done by Professor Joseph making a microgrid in Indonesia, with proposing which is that one, and then can survive different natural disasters that happen. So thank you very much for all the speakers, invited speakers, and thank you very much for all the audience. And I will close this special session by thanking I will close this association. Thank you all of you guys, and back to you, Miss for Miss MC. Thank you, and goodbye.
Yes, thank you very much for the discussion. Thank you to our moderator, Mr. Roni Irnawan, and to our speakers, Prof. Edward from Auburn University, Prof. M. Guerrero from Aalborg University, Denmark, and Prof. Andrew Beckers from Australian National University. Distinguished guests and participants, we are now going to have a break for a while. Just make sure you're not gonna miss the next session, that is parallel session 1 to 5. Okay, the link for the parallel presentation session can be seen in our website www.ict-pep-pln.com. Once again, ladies and gentlemen, the link for the parallel presentation session can be seen in our website www.ict-pep-pln.com. Okay, we will start the session at 1 p.m. Western Indonesia time. So right now I have to say goodbye for a while. I am Santi Zaidan as the MC for this conference, signing out. So make sure you're not going to leave the next session, and stay tuned for the 3rd International Conference on Technology and Policy in Electronic Power and Energy. This event, ladies and gentlemen, is organized by PRSEI UGM and Puslitbang PLN, sponsored by PLN, IEEE, and 4TE. Thank you very much.
Thank you. Thank you very much.